hopefully. Oh, 1 sec. Okay. Hello.
AGT.
How are you? I can hear you, nephew. Thank you, beta.
That's JT.
So what are we doing, Rayhan? Do you remember that? Do you remember that physics question, by the way? That one of the ones that he like didn't count on the test.
Yeah, I know. I saw that text. I don't remember it. Sorry.
It's okay. Because that's something that could be on this thing.
Yeah.
I wouldn't even be surprised if he reused it.
Yeah. That'd be crazy. Actually, that would be crazy.
That would be very like him. So
That'd be,
that's why I was trying to remember what it was, but I can't.
I don't have any specific questions. I was just waiting for anybody else to ask, and I would just listen.
Yeah.
I mean, we should tell the chat that you started it.
Okay. Generally speaking, the 3 practice FRQ problems, whatever had important stuff in them, like properties.
The multiple choice practice ones?
No, like the 3 FRQs or whatever. If you were here yesterday, you probably did them.
Oh, I wasn't there yesterday.
I wasn't there either. Generally speaking, so important things to note. In a conductive surfaces, in a conductive surface of any type or a conductive object, electrons are free to flow within. So if you think about it, like they want to move themselves in such a way that they have like no force acting on them, meaning every particle's in equilibrium. So they arrange themselves to minimize the electric field. So they're gonna have all the negative charges are gonna go to the outside. That's the case for all, or like for most conductive surfaces, like that the charge is going to distribute on the outside, because any point within an electric field is going to have a net charge of 0, and that means there's going to be like no electric fields within it, because they want to be at equilibrium at any point. It's going to have 0. Yeah, I guess, I don't know. 0 electric fields and 0 enclosed charge within, so all the charges go to the outside. For conductive surfaces, it can be uniformly distributed. Also, other thing to note, like conductive surfaces stop other conductive surfaces, electric fields. So like the electric fields from this would stop there. It wouldn't penetrate the wall, but it could like come back outside of it, I guess. Kind of hard to think about. Like assuming this had some sort of charge.
Up, JT.
Hi.
You hear me?
Yeah.
Yo, can we all just like thank JT for putting his time and effort in so we can all
Bro,
do
no
well in
one's
AP physics?
like there's probably 2 people listening. There's no need to think.
JT, you might be the goat of like saving our physics grade. Please, like Rayhan, please say thank you. No,
Thank you,
no.
JT.
You're
Okay,
welcome,
there we go.
Rayhan.
All right. Anyways, what's on this test?
That's a really great question. Like I said,
Is it just Gauss's law?
mostly. Um, what I thought was important to note is like these in that practice, like I said, the practice homework, whatever it was called.
Well, I did them, and I swear I got like half of them wrong.
Yeah, I had to like he didn't actually teach the stuff, so I had to do some of my.
Wait, you think those were like a little bit difficult? Some of them.
I don't think he taught it properly. But like once I GPT'd to understand the properties, it made sense to me. So we'll go over this. Okay. I did this wrong.
Oh, these.
I did it the
It
opposite of
gives
what
us
it's
the
supposed to be.
Q.
This is the wrong way. Like this is supposed to be like this. Because it's a conductive surface. So the reason
Wait,
so
when the R is smaller than A, then it's 0, no?
yes, yeah, I messed it up when so yeah, the reason being is because all the charges are distributed on the outside. So if you drew a Gaussian sphere inside of this surface, it would have no enclosed charge, meaning that the flux is 0. Right? That's a way to think of it. Right?
Oh, yeah.
So like
Rayhan, why do you spell here with HERE?
so like all the
I'm gay.
net charge would be on the outside. So inside, if we drew a Gaussian sphere, the enclosed charge would be 0, so the flux would be 0. So that's why it's 0 in the inside, because electric field, we have E times A is equal to Q enclosed over epsilon naught. So like any enclosed Gaussian sphere within that, it's going to be equal 0 coulombs enclosed. So that means since A is not 0, E is going to be equal to 0. So that's 0 electric fields within. Any point outside, we can use that. We can use the fact that the total charge of this object is Q, meaning you can never exceed Q. So when we have a Gaussian sphere outside of it, it's going to enclose the Q coulombs of charge or whatever. So it's just going to be Q over epsilon naught is equal to E times the surface area of that Gaussian sphere, where R is going to be some variable, and R can be changing, so it could be bigger than the radius, or which is A, or it could be smaller. So when it's bigger, R is the radius, we divide Q enclosed over epsilon naught by the surface area, which is 4 pi squared for a sphere. That's something you could memorize, or you could rederive it somehow.
Wait, I have a question. Can a Gaussian surface like encapsulate multiple conductive or multiple objects?
Sure, but the reason we create the Gaussian surfaces is because they're supposed to exist such that all their surfaces are perpendicular or parallel to the electric fields. Otherwise, we get weird angles that are really confusing.
Oh, so if you had multiple objects, it wouldn't be.
It could work if we have let's say we have 2 cylinders and they're not touching each other, right? But if they're like
Yeah.
the 2 cylinders, we
Yeah.
could make a bigger Gaussian cylinder over both of them, and that would work. But if they were different shapes, it probably wouldn't work. You could do like a cube and a rectangle. That would work fine. You could do a Gaussian like a rectangular prism over a cube and a rectangle. If we have like a cube.
Well, I thought Gaussian cube would not be uniform.
Why not?
I mean, sorry, it wouldn't be perpendicular at all.
Let's look at it.
What?
So if we were to draw
We never did that, did we?
I don't know.
I know we did. There's one that's like
We
on like
probably
a
wouldn't do it.
on like an infinite charge sheet or something. Do
That's
you know that one?
That's what I was trying to find out. I couldn't find that. Was that what
There's
was on our
it was
quiz?
an Albert question.
Okay, Albert question.
I don't know the number, but you could if you search through, you'll be able to find it. Like if you just spam through.
Yeah, 1 sec.
He specifically mentioned it to me. I'm like, he's like, you should know how to do that. I'm like, oh, okay.
Yeah.
Meaning it's probably on it. I remember
Very
the
long
answer was
wire.
it's like 2 over 6e. I don't know if it's the wire. I think wire.
Oh,
you use
it was
cylinder.
a cube. Yes, it was a cube.
Yeah, don't you use a cylinder for a wire?
Yeah, you can.
Like an infinitely big cylinder. I don't.
I think I got it wrong, but I don't remember what was it, the unit? Charged in a box? No.
I can't see that, to be honest.
I know, but I don't know what it was.
Oh. It was like somewhere in the middle.
Is this the correct one to practice?
Is this? Yeah, probably.
This? Oh, yeah.
Yeah, this one.
Sure. So let's see if I can do it correctly. Okay. So a charge, okay, it's fixed 1s. Okay. What is the value of the electric flux that passes through the square? Okay. Okay, so we're gonna make a Gaussian cube over the surface. So we have a surface with that's a square surface with side
Aren't you
length
supposed
s.
to? I thought you're supposed to use like a cylinder, no?
You can't use a cylinder because
No, but like a backwards, like a not backwards cylinder, like you could tilt it 90 degrees, no?
you're right. It could be you're saying like up this way.
Yeah, I think that's like the easiest way to do it.
Well, let's try it with a cube first and see what happens. Okay. So we're gonna make a Gaussian cube around it, like such that all the surfaces are gonna be.
The way a cube works, it's not going to be easy to solve.
We'll find out. We'll see. So we have that. What are we finding? What is the electric flux? Okay. Flux is Q enclosed.
Cool.
Times what's the surface area of a cube is 6 times the side length, right?
Is it? I don't know.
Well,
6s.
6 times the side length, yeah. 6s. Okay. Well, it's side length squared, actually, I guess.
Yeah, it's also 6s squared.
Okay, equals Q enclosed over.
Epsilon naught.
Okay. So our Q enclosed is going to be Q. And let's see what's wrong with this, why this doesn't work. Let's see what's wrong. So obviously there is something wrong here.
With that being said, I probably would have just done this and probably still picked D based off what's on it. But the s squared was can you solve for that? And where does the 1/2 s come into play?
That's a good question. So 1/2 s would be like if we drew a cube, 1/2 s would be half the height of the cube. So like we're gonna imagine the plane, like the square, is like halfway up the cube. So it would be 1/2 s plus 1/2 s.
Okay, but in a cube, the field lines are not like going to be easy to solve. They're not perpendicular in a certain way. And if we use the like cylinder standing up, it's just pi r
imagine
squared.
that the square shown in the is a face of a cube. Okay.
What?
Yeah.
Damn.
So in the solution, the charge, okay, is at the center of the cube. Okay. Oh, okay, so symmetry. So this is a very different type of question, all right? So the net flux is Q enclosed, right? Over epsilon naught. We agree on that. It's the net flux, okay?
Because it's a point charge, basically.
Because it's a point charge within this cube, like it shows, right? So that's the net flux.
Yeah.
But we also know that the net flux is equal to the sum of the fluxes of all the surfaces. So that means, and it's asking for the flux through the bottom surface. So since each surface is at the same distance from that particle, right? Each surface is at the same distance. That means that the net, so each of these surfaces is going to have 1/6 of the total flux, right? Since there's 6 identical surfaces.
But isn't the direction different?
The direction's different, but they're all the same distance from.
Yeah.
So it doesn't matter.
Is it a magnet? Is it a scalar?
They all have the same. Yeah, it's a scalar. Flux is a scalar.
Oh, okay. Never mind. Yeah, that makes sense.
Yep. So since there's. Well, 1 sec, Nico.
So they're basically all like s squared.
Yeah, since the net flux is Q enclosed over epsilon naught, but there's 6 identical surfaces with identical distances, that means each one is going to contribute 1/6 of the net flux. So that's how you get your answer. There's really, I can't think of a better.
That's not that bad.
I can't think of a better way to. You could do it with like some trig identities.
Yeah, but that's pretty easy, honestly.
Yeah.
Oh, Nico's in here?
Yeah, 1 sec. Okay, let's. Here.
So the IQ is basically just increasing a lot right now.
I'm so cooked.
That's okay.
I was just studying for like 2 hours.
That's good.
I kind of got
it.
it.
For like 5 hours and I got it less.
I actually got more, off the Gaussian like stuff, but that's gonna be more on the FRQ of Thursday.
No, that's gonna be a lot of MCQ.
It's gonna be a lot of MCQ, but like the magnetic flux stuff, or the
What?
not the magnetic.
That is Gaussian.
Flux. No. Like there's like in the slideshow, there's two separate sections. There's flux and then there's Gaussian surfaces. It's two different things.
Yeah, but flux is not without Gaussian is easier.
So also there was an
It's really just
equation.
E times A cos theta.
Enough, Zach.
Let me see this. There was some. Let's see what these were. Yeah, let's do this. So this type of question we could definitely see on the quiz or test or whatever it is. This is super easy. From the reference table. The reference table gives us this equation somewhere that Mr. Huang didn't teach, but of course we have to know. Q total is equal to, so it says Q total, like total charge.
Rho of R can be changed for any of the mass densities, right?
What happened?
Like rho of R can be interchanged with any of the mass
Yeah,
densities.
it could be sigma of R, but then it would be sigma of R dA
Yeah.
or lambda
Right.
of R.
And then it would be
Yeah, I'm just helping out Nico
DL.
because, like, of course I mean.
Okay, so
What happened?
anyways, so can we continue this? So here, so here we have, like, this is straightforward. R is gonna go from, well, instead of R, they use A as the variable thing, right? So we're gonna have Q total it's asking for. Total is equal to, rho here is gonna be CR, and it's gonna be dr from zero, from, I don't know why it says 0 to A.
But wait, it's not dr, it's dv.
Oh, you're right. That's what it is.
If it's converted,
So
yeah.
it's dv. And so why this is important is because v equals sorry.
Oh, it's because rho equals Q over V.
The big R is not even relevant to this question at all. I don't know why they give it to us. So v equals 4/3 pi r cubed. How we do this? Little r cubed. So dv, okay, is 4 pi r squared dr. Okay, that's just differentiating, right? dv over dr, that's what we're saying, right? dv over dr. Okay, so we can substitute this in, okay? So we have Q total equals, and these bounds were not correct, equals, what was it? So CR, right, from 0 to A is the maximum, times 4 pi r squared dr. Okay. I'm going to pull out all these constants, so that's going to give us 4c pi, that's how I wrote it, I don't know why, 0a r cubed dr. Okay. When we evaluate that integral, that's going to give us c pi a to the 4th, which is our answer.
Oh, okay, that makes sense. Wait, is the Gaussian sphere here, is it the solid line or the dotted line?
There's no Gaussian sphere at all. So the reason, well, you could,
says,
sure, okay, so what the reasoning there is a Gaussian sphere is because we're finding the enclosed charge as like a based on the volume, but like the Gaussian sphere would be it's actually neither of these. It would be a bunch of spheres. You would have to have a bunch of spheres because it's dv.
Just a cross section of it.
It would be like
That's what
A.
it
It would be the A maybe, but it's actually
No,
from
it literally says it. Look at the last sentence of the
yes, I know.
explanation.
Of radius A.
It's cross section of the sphere up to radius A.
Yeah. So the charge enclosed is that.
So the actual sphere itself is like
it's big R.
The big R.
But that's not
Big
relevant
R,
to this
okay.
question.
No,
It could be in other questions though.
Yeah, that's why I was asking.
Yeah.
You always use little r for the Gaussian sphere, and whatever they give you for the actual sphere. All right, why are we being quiet?
What? Do you have a question?
I don't know.
Like there was a bunch of these on here. I think they were all the same thing.
All the questions on the Albert are the exact same thing, just different format.
Yeah, the Albert is not that bad. The AP Classroom, I swear, was like impossible.
If an electric field at all points on the Gaussian surface is 0, does that mean the net charge is 0? No. Yes. Let's see. On a Gaussian surface is 0. Okay, so that means the field. Yeah, that's just
on all points of the closed.
That's just common sense since E is 0 everywhere. The charge enclosed sphere.
It's basically saying each individual point on the sphere is 0, so the total is 0.
Yeah. E dot dA is 0.
That's a trick question because usually the net is 0, but there is
But
obviously
the
each point isn't.
if it asks if the charge is 0 everywhere, that could be false. Okay, AP Classroom, you said?
I don't have like specific ones, but like most of them were just not it.
Do
Okay.
The Albert was way easier, bro.
Yeah, can you do the Flux AP Classroom? Because I did the first.
I did the
three
progress. I did
questions.
like the progress check one, and that was
There's a
not.
flux. Yo, my scores are so horrendous on AP Classrooms, but sure, let's do it.
Yo, if JC is dropping 40s, like what are we
No,
expecting?
look at this,
what
look
is
at
he
this, look
expecting
at
us
this.
to
Wait,
do,
wait,
bro?
watch these scores. Wait, where is it completed? All right, let's see.
No, you're in
16
mechanics.
Okay, wait. I know, that's what I'm showing. 2 out of 9, 4 out of 9, 6 out of 9, 8 out of 9, 7 out of 9. It's because I
So
don't.
what does he expect from us, bro? We're
Okay.
dumb. You're
No,
like
that's
the
just
smartest kid
that's
in
just
the
because I
class.
speed run it. Was it one of these?
All right, Zach, just glaze him a little more. Maybe it'll help.
No, no, you have to say thank you that he does these like for us, so
Okay.
we can like pass.
All
Okay.
right, which one? What are we doing? Active or completed? Electric
Yeah,
flux
do
quiz.
the progress check one, bro.
8.
Okay.
Because that's like everything.
Which one? This?
Yeah.
No, but he said the stuff like that was on the other quiz isn't really gonna be.
When did he
on-
say that?
He's told you, Zach.
He did? I don't remember him saying that. He said like it's
he
still
said that
on
it's
it, but
gonna
obviously
it's still
Gaussian's
on
gonna
it,
be-
but it's gonna be more based off the
It's
new
okay. Most of this
schedule.
is Gaussian on here too. This one is easy. Like we don't have to do this.
Attractive balls. More attractive
Hello?
balls.
What?
What?
Okay, yeah. Well, this one is what again?
You want to do this?
Sure, go on.
What is okay? A point charge is located at negative 3x. A hollow conductive sphere, a radius 2x0 is located with its center. Okay, as shown in the figure. Both the point charge and the sphere have a net charge of q. What is the magnitude of the electric field at the origin? Okay, so you got to do these separately. So like the magnitude of the electric fields. All right, so caused by that point on the left is going to be k q over 3x0. Well, it's 3x0 squared because it's from the center, right?
Oh, is it from the center of the sphere of the hollow sphere or the center of the sphere?
What is at the origin? It says the magnitude at the origin.
Okay.
So this is gonna be in the negative direction. So that's the first one. Now we gotta find the electric field at that point. So how we do that? We're gonna use a Gaussian sphere. Okay. E times A, which A is 4 pi little r
Are
squared.
you writing this out? Because
Yeah.
like we can't.
Yeah, my bad. So this what you see right now I've written so far is ignore that. This is from the point. So that's from the point at negative 3x0. Okay, that's the electric fields from that point. All right. So we're going to have to add it on to the electric fields from the sphere. So the electric from the sphere is we're making a Gaussian surface inside of it. And the radius of the Gaussian surface is going to be from x0 to the origin. So that's x0 is the radius. Because that's the Gaussian surface that we need. Okay, times, what was it? Net charge of q over epsilon naught. Okay. So, yes is q over 4 pi. And the distance from x0, which is the center of the circle, to the origin, which is the point we're testing, is x0. x0 squared. Times k, I guess. I know, we already have that. I'll make this over 4 pi naught. Okay, and since that's positive... shoot, this is the wrong direction. Okay, since that's positive, it's going to push it in the negative direction. Okay, so we're going to add these together. Q over, what is that? 9 times 4 is 36 pi epsilon naught x0 squared plus, minus Q over 4 pi
Epsilon squared.
x0 squared. Okay.
Which is 8.
Multiply this by 9 over 36.
Oh, sorry, 9. That's 8.
So we get
9.
negative 8 over 36, I think, right?
It's a magnitude, right?
So, yeah, let's see if this is right. Negative 2 over 9.
That's wrong, bro.
Oh, no. How did we go wrong? Let's see.
Think
4 pi.
What part?
The Q and they
Oh,
both have the
'cause
same charge, right?
um from from the
Oh,
origin.
oh, no. It's a hollow conducting sphere, not an insulating sphere. Meaning at the origin, it's gonna have 0 electric field. Meaning we
Why?
didn't have to do, cause that's the
Wait, so
property.
any point on the inside of that hollow sphere is 0?
Yeah, electric field and charge contained.
Oh, because it's conduct. Wait, why? Can you explain why? I'm sorry.
Because
Because
that's
it's
the
conducting.
property of conductive objects is that all the charge distributes onto the outside of the surfaces.
Oh,
So the
anything on
electric
the
field
inside,
and the
right?
Q enclosed everywhere is 0. So
But so if this was a solid conducting sphere, it's still 0.
if it is a solid conducting sphere, it's just that all
No,
the
it's
charge.
hollow. It's hollow.
I don't even think that makes it oh shoot, wait, that means this does still have a field. Crap. No. So, I'm thinking. The answer is 0.
What?
Okay,
Yeah,
this is
because the origin, it's conducting.
okay. No, this is really.
No,
I
what's
think.
this here?
I'm pretty
No,
sure.
but the
Listen.
point mass, the point
Zach,
charge is
shut
still.
up! Oh my God, let him
Oh,
explain.
chill. The point charge is
Holy
still has
shit!
a force on the
No,
origin.
it doesn't. You're not letting me explain. A property of conductors is that they interrupt the electric field of other conductors, so that electric fields wouldn't actually get through to the origin because the origin's surrounded by this other conductor.
Wait, what? Bro,
Yeah.
chat did not say that when I
Oh,
did this question.
well, I believe the answer is 0. What did chat say the answer is?
I don't remember, but let me quickly ask
Check.
him again.
Ask him like it's a
Let's see.
person.
Unless in which case the only other alternative is that the electric field is only from the sphere, but I think the electric field of the point is canceled out.
Let's see. This chat is saying origin's inside the hollow conducting sphere, so E is 0.
Yeah. Okay.
Yeah, actually, yeah, it did say 0. Okay, my bad.
Oh, would you look at that, Zach?
Well, no, but I swear the first time I did it, it did not say 0. Sometimes it changes up.
Okay, so
See, that's
I
like a
want the
trap,
reasoning.
though,
The reasoning is there's 0 charge enclosed at that point O, from this conductive sphere, because it's all the charge is outside of it from that Gaussian sphere. But then the other thing is that that charge, that point there, it's not going to exert any field strength on it, because this surface actually interrupts it. The other conducting sphere interrupts and blocks the electric fields.
Can it go through an insulating sphere?
I guess theoretically yes, but like that stuff's starting to get convoluted and I don't think they would put us through that.
Okay.
At 0.
Fair.
I
Fair.
really should have read the question better, and considered that fact, but I would have got it eventually. If it was a free response, everyone would probably get it wrong, but like
Wow.
if you figure this out and you notice that it's a hollow conducting, you could instantly say 0. There's no math that has to be done for this question. Oh.
Respect.
Oh yeah, this one sucks, bro.
What the hell?
What the? Don't. He's not gonna put this on there. If he puts this on here, there's no way.
I tried doing it, and I think the answer is B.
Should I
To be
try it?
honest.
I
Yeah.
highly doubt he's gonna put that on there.
Well,
Try it. Wait, I mean, this is like you have to do the semicircle like thingy again, or is this a different
Let's
type of
see.
question?
I haven't read it. 2 circles represented by the dashed lines in the figure are concentric with their common center point at C. Along the right half of each circle is a thin, insulating semicircle containing a net charge. Ugh. Okay, has radius r uniformly distributed charge plus q, and the semicircle of radius 2r has uniformly distributed charge. Okay, so how we can achieve this, right? We have 2 things here. We have E net, okay, but we only have the x component because we know the y components are going to cancel out. I think.
Right. I think they should. And the semicircle,
Actually, let me see.
it did cancel out.
So,
it would be like,
well, let's see.
bro, you know it is. Every single answer choice has integral sine theta.
Okay, just stop talking. So we have k, q. Well, q is right. Over 5. Well, let's see what the different options are. I think it's just gonna be 5/4. The reason is because
No, but the charge on the top is negative.
oh, you're right. So what is that? Q minus 1/4 is 3/4. It's probably that, right? We should probably go through this. It might be smart to go through this. Lambda equals dq over dr. Dr is the circumference equals big R d theta. So, but this is also equal to the cosine component. I don't know why that would be sine. Oh, I guess it depends on where theta is a reference point of.
I don't even get sine and
It's
cosine
just
at all.
you don't even have to know what function it is.
Well, in this case, it tells you basically, but like a FRQ, you might have to.
Yeah, it would have to say where the reference point is.
Mm.
Yeah, stupid question. I don't think there's any practicality to it. Like,
But when is there ever practicality to these problems?
oh.
All the time. No, please don't, JC. Please don't. No. No.
A figure shows an equilateral triangle. Vertex. Oh man. Oh.
Yeah, I'm telling you, these were so annoying, bro.
D. Okay. Y. Okay. So, and the area has the components AX. Oh, it gives us the area.
Yeah, but like you still have to know how to do it. Like some people, aka me, don't know how to get the area from that.
I think it's just this. Can you put this into chat?
I did. I remember. I don't remember what the answer was, but I think.
Can you check your
Let me
history?
check, yes. I'm gonna do it real quick. I know there was some like weird formula to get the area, and then it was I don't remember how they did that, and I don't know how Mr. Huang thinks we're gonna be able to do that.
We're not, bro. If he puts anything like that, he's gonna chalk the
Bro,
question.
okay, so what it does is it has area vector components. Only the x component matters. Find the triangle's area, so it's square root d squared plus d squared d rad 2. And then area of an equilateral triangle, rad 3 over 4 s squared. Substitute in that d rad 2, I think. So 2d squared times rad 3 over 4, rad 3 over 2d squared. Each a of x is equal to a over rad 3. So 1
What's
over square root 3 times square root 3,
final
1
answer?
half. Yeah, 1 half.
Oh, look at that. I did it. Okay.
Bro, how did you get that, bro?
Oh,
Nah, you're pissing me
so
off.
the way I did it is since the electric field is in the x direction, right? We only want to know about the surface area aligned to the x direction. So I took that triangle we had, since the triangle is like this, it's something like this on those axes, and I took it and I flattened it such that I only looked at the surface that's perpendicular. So like if we look at that, right? It's d tall, d wide. So look, we have a new triangle here. So I only looked at the area of that triangle. Like that's formed. You see that
Oh,
upper like triangle part that's formed by this equilateral? Like this part here. I only looked at the area of that, and that area is gonna be 1/2 d squared. And then I just multiplied that by e0.
I'm sorry. How is Nico B supposed to be thinking of that? How is Zach S supposed to be thinking of that?
I don't know.
You know, how Connor Wu gonna come up with that theory
Oh,
during
he's not.
like none of us are doing that. If Ben and you do it, that's fine, but like no one else is getting this.
You just imagine, since the electric field's in the x direction, imagine your camera's on the x axis, like looking towards the triangle. See what shape it would look like. It would look like this.
Bro, if I have to imagine that, like
Yeah.
it's already over. It's basically
It's
over.
1/2 d squared.
Maybe Max will know in the call now.
Yeah. Let's see. Okay.
Guys, there's no way the multiple choice is gonna be this hard.
Well, this
Yeah.
one's not actually hard. That's the thing. So he could put something like that on there.
Bro, the last one.
I don't know. It's interesting that AP Classroom's harder than Albert this time. A long
Bro, he
insulating.
used. No, the problem is he uses AP Classroom for his
That's why I'm
problems.
reviewing these. A long insulating tube of length L has inner radius R.
What the
So it's an insulating tube meeting charges uniformly distributed probably. Oh no, it has a charge density. Okay, as a function of R. Okay.
Wait, this is not bad.
If charge is uniformly distributed, isn't it always for charge? Wait, isn't it? Oh, charge
It's not
density is
uniform.
It's not. No,
constant.
Max. It's Max. It's not. He made a mistake. It's not.
So
Okay.
so we're gonna look at the Gaussian. We're gonna make some Gaussian stuff here. Electric fields inside. So E, we're gonna make our Gaussian surface is gonna be that circumference or whatever, the surface area of the Gaussian surface. That's parallel. I want to. That's
Parallel.
perpendicular. It's 2 pi RL is gonna be equal to. So now what we have, charge enclosed. Okay. How do I want to do this? I'm thinking. Does it not have L as a factor here? What is the electric? Let's see. Oh, so this is dV. Okay, that's what it is. So it's
You
gonna
just
be
do it from.
beta R cubed dV. Okay, and V is equal to pi R squared L. Okay, so dV is 2 pi RL dr.
dr.
So we have E times 2 pi RL equals this integral beta R cubed times 2 pi RL dr over epsilon naught. Now I'm going to cancel out the 2 pi. I'm going to cancel out the L. Cancel out the L. Okay. So we have, yeah. Actually the only issue here that I just noticed we have an R there. That's
You need your bounds, bro.
I think that R's got to, yeah, we will. I think that R has to actually go into it. I think that R can cancel out, if I'm not mistaken. I might be wrong.
Wait, I don't think that because you have to integrate
but
first.
that's but that's the R. That's the variable R. That's
no. Look. In the answer choices,
Wait,
the
you're
R
right.
is outside of it.
Okay, so we'll keep that out there for now. So E times little r is equal to beta r to the 5th over 5 over epsilon naught. So let's see if this
Wait,
is.
yeah.
We're gonna let's just see if this is correct first. Times so beta r to the 4. This might be wrong depending on.
It's wrong because it's not 0 to R. It says from.
we didn't do it yet. That was an indefinite integral. I didn't evaluate it. So now we go from RB to. Oh no, it's just R to RB.
Wait.
Oh no, it's RA.
Wait, how do you know? Sorry.
So is it what's the correct answer according to?
From what I remember, I think it was C.
It's C.
From what I remember, yeah.
Dude, just say what the answer from what I remember.
I don't, bro. I did these like an
then
hour
check
ago.
it. My God.
Yeah,
Okay.
you have to give me a second, bro. I don't have this on the top of my head. I'm not
the
like.
actual reason is like for this row, little r, we should actually replace it with like some other variable because it's redundant. We should actually have it as like E times R. It's C. Yeah.
Yeah.
E times R. This is how we should actually have it. It should be from RA to R, and then row should be replaced with like some other value. Like we can make it like M. So it's gonna be beta M to the 4th dm, because the variables were actually redundant there, and that's super confusing, but that's how physics does it. So when we actually evaluate this, it's much easier to understand.
Bro, I think the other one was fine.
So well the variables were redundant before, but now they're not because we replaced R in the other thing, which was confusing. So that could lead to you getting the wrong answer depending on.
Wait, so how do you know it's from RA to R? Because I thought it would be R to RB because it says it's R between RA and RB.
Well, it said between, so it's going from R to no, but it's asking for it as a function of R.
So what does that mean? What do you mean?
So
What is
Basic.
electric field E when R is greater than RA but less than RB inside the tube?
Yeah, so it's saying what's the electric field in terms of R while R meets this requirement. This function works. So like it's saying that E is a function of R.
But doesn't R meet that requirement from all values of R to RB?
What?
The requirement.
Why
the
are these
range
questions
given
so
from
hard,
R
dude?
to RB?
Bro, this is
Right?
literally this is all it's asking for. This is the situation that applies here. E of R is equal to all of that over R, little r. So like there's nothing more to it.
I'm just okay. Whatever. Yeah. Fair. Whatever. what can we do about it, bro?
Wait, JT. How would really quickly? What was I
There's
gonna
no
say?
really quick.
So, so if it's non-uniform, if it's non-uniform charge, you would just use a normal
We
integral to
just
do
did
this.
that. It was just non-uniform. We just did that.
No, I'm saying like you would just use an integral to do
Well,
this,
look
right?
at how
Because I had to.
look at how I just did it. I just,
Yeah,
Where?
Max, can you lower your?
I just used an integral. So yeah.
Okay.
Sorry, bro. Like that one's not that bad. I just don't understand the bounds.
Yeah. Okay. Sure. So the reason it's from R to RA is because
First of all, isn't it RA to R?
okay, no, it's R to RA. So the reason is that basically, look, if the point of the Gaussian cylinder was less than RA, that means the enclosed charge would be 0 and the value would be 0. So this would not evaluate correctly because it's not going to be 0 for all values of R that are less than RA. So if the little r was less than RA, then it would be 0 for all values. So this function wouldn't work. So we know that R has to be greater than RA. So the inner bound of this integral has to be RA because it's the accumulation of all those Gaussians, like Gaussian, whatever you want to call them. I don't know. It's just
Wait, so is it RA to? Oh, okay, got
it's
it.
just
Never mind.
you just
Okay,
gotta
that
think
makes
about the
sense.
charge enclosed is from the
Oh,
radius of
okay.
R
That
is RA to R.
actually does make sense.
Yeah.
Yeah, that does make sense.
And it's not RB because RB is the outer bound, but we're looking within the two. So if RB was one of the bounds, like if we evaluated this from
So R approaches RB. It's
yeah,
true.
exactly, it can approach it, but it doesn't necessarily
Okay,
it's any value between RA and RB.
true. That makes sense actually.
Yeah, so if we like plugged in for R, we plugged in RB, then we would get RB minus RA, and that's what we. But we could plug in for other values of R too, and that's why this is nice.
So. Let's see. Moving on.
One sec. Let me see what Mahin was like complaining about.
I was just crashing out, bro.
Wait, what did Mahin do?
Nothing. He was
Nah,
just
he's just flipping out.
he was looking at the
Also, this is only half of the test, so like if you just know this like 80% or like 70%, bro, you just lock in for tomorrow. And it's also square root curved. So like
it's
no,
also second
Max.
semester.
If you know physics 70%, then you get all of them wrong. In my experience.
what?
What are you
Like
saying?
if they're because usually they put trick stuff. So like if you think you know it, but then you're always gonna fall for the bait every single time. You get like a lot.
I don't know,
why-
bro.
That's
I
why
disagree.
if you didn't study,
And
you
then
look at the question
question
and you're
they're all-
like,
Now I
like,
can't
on
hear
the last
anything.
one, I had one wrong concept that like I just messed up every time, and there was multiple questions about it, and I got all of those questions wrong.
Bro, this is not a
can't just
statistics
diversify it.
test. We're not talking about the probability you get a question right or not. It's irrelevant. Just know the stuff. You're not gonna play you're not gonna win by playing a
That's why I'm
statistic.
here, bro.
You're not gonna win by playing a
JT.
guessing game.
We're not like you, bro.
This is it's nothing to do
We
with
have to
what
We,
game
you
we
it,
know.
don't have this
We
much
have
time
to.
on our hands, bro.
I've
No, it's
done
not even time. We just
I've
don't
done
have the knowledge, bro.
I've done the same
I
studying
have the
as
time. I'm just retarded.
no, but playing the statistics game is not gonna help you. Just do your best. Like that's it.
I mean, Zach Lee got an 88 from that, so.
Okay.
I had a 79, bro.
Yo, if you ever don't know the answer, just put C.
You're welcome to. If you just guess all C's, statistically speaking, you're gonna get a 50 on the test. So
That's not even like horrendous too. That's like that's crazy.
Just ace the FRQ.
Actually, no, because FRQs were 50%.
yeah. So AC
Alright,
FRQ. Okay, let's do
This
this.
one should be
X
right.
and Y are
No,
made of
no,
different.
no diagram means it's easy.
They are electrically neutral and isolated from other objects. They are rubbed together, after which X has a net charge of -5. So what that means is that X gains electrons. Nothing can gain or lose protons. Protons don't move. So since X is now negatively charged, that means it gains electrons. So that means Y loses electrons.
See, this
Wait,
is the
what?
type of questions we need, bro.
Nothing
This
can
is the
lose
type of
Wait, go-
questions that Mr.
protons.
Huang
Don't
Wait,
used
wait,
to
wait.
on it.
Wait, go back. They made it are electrically neutral, and then sphere Y, loses electrons. Okay, that makes sense.
This is a question we had in 7th grade. So
No, Mr.
Wait,
Huang
it-
better lock in and make the whole test this question.
Mhm.
So sphere X loses, sphere Y loses electrons because of giving it to sphere X, and then
yeah, since
something like that.
sphere X goes negative, that means it's gained electrons.
Sphere X is
Electrons
taking
make
those
it
electrons
negative.
like a good
So
boy,
sphere Y's
and
lost them. Yeah.
But
Like
why
Isaac
does it?
Newton.
Why is it a positive net charge then?
Positive means you lose electrons. Because if you're
Yeah, you
neutral,
can.
if you're
protons don't
neutral and
move.
you lose the negative elements, you become positive.
Oh, okay, that makes sense.
Like minus a negative, you get a positive.
Mm-hmm.
Okay, what the hell is this? A hydrogen nucleus experiences a force after entering.
This one's stupid, bro.
Enters the same thing. So the electric field is going to be independent, right? So we know it's either A or C. Okay. Because the electric
this
field
is
is
what I didn't
independent of the second
realize.
charge, but the force is not independent. I messed that up. So it's going to be C. Because force is Q1, Q2, but electric field is just Q1, and Q1's it doesn't change.
So electric field is constant.
Wait, let me see.
Yeah.
yeah, because it's no JT. It's force times charge. That's definitely what it
this
is.
fine.
No, it's F over Q, not F times Q.
Okay.
No,
This looks much more interesting. Okay, a
No,
curved
this
piece of
is
insulating
ass.
material is in the shape of a 120-degree circular arc. Okay.
This is one of the worst questions.
The insulator has. Okay, this is not bad at all. The magnitude at the center is most nearly cool. So we're gonna use some symmetry arguments here. We know that the the y component is gonna be 0. Okay, and the x component is gonna be k q over r squared, where r is the distance, which we're given is 0.2 meters.
it's just r. It's just r cosine of theta.
And then
I think.
this is gonna be
Or
actually.
Yeah. It's r cosine of theta is
Let me make
the
this. Shh.
thingy.
Yo, Max, your mic is so loud, bro.
Yeah, your mic is very.
Is
loud.
it really?
Yes.
Yeah.
Let me.
You're like,
How do I lower it?
bro?
I don't know, bro.
How do I?
By muting yourself.
Just don't talk.
And since we only want the x component is the cosine component.
Better.
Somewhat.
Okay, good. I lowered the volume.
So dq is equal to. So how we're gonna do this? Dq equals lambda dr. So we're gonna substitute that in. So E of x is equal to k over 0.2 meters squared. So now we have lambda cos theta.
Isn't lambda ds?
dr. It's dr where r is like some little length. We can make it like dl instead.
Yeah,
Sure,
but
we'll do DL.
don't. Isn't this the one where you do like ds
I'm
equals
doing it,
r
I'm
d
doing
theta or something?
We'll make it ds.
Oh, sorry.
ds is the length of the. S is going to
The
be the
arc
length
length.
of the arc length, exactly. So ds, that's what we'll do. Okay, but now we got to get this in terms of theta. So we know that arc length, we have a formula called SOR. So arc length is theta big R, where big R is the radius, right? Or in this case, it's 0.2. Okay?
Wait, JT. Why is this in terms of the arc length?
Because
Look at it.
It's
given a
DQ.
linear
Oh, I'm
density.
retarded. I'm retarded.
We know.
Okay,
You
I'm
don't need to
retarded.
keep spamming that. Thank you. Okay.
That's a YouTube channel that's public,
So-
and actually that
Oh
word
my
is really
God,
offensive.
Zach! Enough.
Okay.
No,
so,
some people actually have disabilities and they don't want to hear that word. It's
Okay,
really
No,
offensive.
because all you do is talk.
Great. Okay. Anyways, S equals theta R, so ds is r d theta, but this big R is the constant 0.2 meters we're given. You can wait till we're done with this question, then you'll ask your questions. So ds is 0.2 meters d theta. So now we finally have this in terms of d theta. So E of x is equal to k over 0.2 squared times lambda times, we sub this ds in with this stuff here, times lambda times 0.2 meters, all of that. So we have cos theta d theta, and we have our theta here. This is going from, let's say from this starting position here, that's 60 degrees, so that's 180 minus 60, so this is going to go from 120 degrees to 120 plus 120 to 240 degrees. Okay. Yeah, I'll just invite you so you just stop. Anyways, don't talk too much.
Wait, how do you get those bounds?
Those bounds, that's the angle. I started the angle relative to the horizon this way. So like the angle from there to there is gonna be 120.
Oh, okay, gotcha. Yeah.
So I'm gonna convert that in terms of pi. So what is 120 degrees? That's 2 pi over 3. Right? And then this next one is gonna be plus, that's gonna be, I think
Negative 1 over 3.
4 pi over 3.
Negative pi.
4 pi
What?
over 3. 4 pi over 3. It's starting from the horizontal, bro. The angle, the angle is that. It's 4 pi over 3. Okay. Anyways, so those are bounds. So when we evaluate this, let's see if I actually did it remotely correctly. K 0.2 times lambda. Does it give us lambda? Yeah, it does. Lambda times, so cosine, that becomes sine. Sine of, what's sine of 4 pi over 3?
I don't know.
Minus
We get a
sine of,
calc.
well, we can just look at it on this graph. So 4 pi over 3, that's going to be rad 3 over 2, I think. Rad 3 over 2. And then the other one's going to be negative rad 3 over 2 minus
Rad
3 over 2. Okay, so that's going to give us rad 3 is that value. So now let's rad 3. So now let's plug in all these values into Desmos. We have k is equal to 9 times 10 to the 9, I believe. So k, so now we have k over 0.2 times lambda was given to be, what's lambda, is 2 times the micro symbol, which micro is 10 to negative 6. Okay, rad 3. Is that even an answer? It's probably this one. It says most nearly. So 155,884 rounded up, 160,000.
Tough. You think Max knows that he got kicked out? He's probably still talking.
Probably.
Oh, my brain is fried, bro. I don't even feel like studying for this anymore.
Yeah, there's not much more to study.
Is there? So, like, do you think
All right,
know,
wait,
like,
hold on, guys. I just have to say something. I was literally speaking.
We know.
As Zach said that. How did you know that?
Because you're predictable and cyclic.
Yeah, Max, I know you, bro. Wait, JT, you think there's gonna be like 8.4 stuff? Like we had to derive this stuff. Like I know we had the ring problem before, or like the semicircle problem before. Yeah. Like, do you think there's gonna be stuff like that?
Probably.
How would we go about doing all that again?
Zach wasn't here that day, so he has no idea how to do it.
For the ring you want to do?
Yeah, sure. Go on. That's like the hardest one, right?
Whatever. I don't know.
Like the wire is light, but like I guess we can probably do that.
No, do the ring.
Let me open up the reference
here.
I don't even remember the
ring. Shit, so we're cooked?
No, I can do it. I did it like 20, 30 minutes ago. It's fine.
Wait, what? No, that was semicircle, no?
Oh, whatever. They're all the same to me, bro.
No, they're not. Okay. This one you have to do like square root x squared plus r squared to the 3 halves or something.
Okay.
Yeah. All right, JT, do it for what's it called? What's a hypercube?
I don't know. Oh, for 4-dimensional. I can still do that. It's just gonna be harder to parameterize or whatever.
You can need some triple integrals.
Yeah.
Please do not do that.
All right, so let's see. So we're doing for this ring here. I mean, that's the same as like, almost the same as this semicircle. Okay. So let's recognize that we have we're only gonna look in the x direction. That's the important thing, right? Only this direction, because the y directions will cancel each other out. So remember that x is equal to the x of a vector, right? Vx is equal to v cos theta, right? So that's important to note, okay? So we're gonna put a cos theta here for now, times k over r squared dq. That's our equation for, okay? So r squared can be replaced with the radius here, which is a. Actually, no, it can't. I'm tripping. The radius is little r here, which little r is the square root of a squared plus x squared. Okay, so we have square root of a squared plus x squared dq. Okay. Now what's also important to note is that none of this is in terms of dq, right? Is not in terms of any of these variables. So dq, you can just evaluate that to become q, because it's not in terms of the position or anything. It's not relevant. So, because the charge is the same everywhere for all values of theta and a of x. So it just becomes q here. Okay. Now, what else?
JT, you're just saying that because you're defining like an arbitrary charge where it's like
the charge is
it's not
uniformly distributed everywhere.
Yeah, it's not dependent on anything. So you're just defining it as q because why not?
Well, it says q here, so dq evaluates the q. If it gave us a density, we would
Wait.
use it instead.
I swear you had to do the arc length thing on this one.
Yeah, wait, now I'm confused. Wait, so you said dq evaluates
Instead of cos theta, I think you do x over r.
Look, so dq, let's see, dq, okay. Well, that would give us a density. That's the issue. That would give us a density. So we'll do that though. We'll do that. Is equal to lambda dl, where that's the arc length, okay? And L arc length is equal to theta r, all right? But actually, this is a different theta. It's a theta around this way. So we have to define it as another variable. That's why I didn't want to do that.
Wait, can you say cos theta is just x over r or something like that?
Yeah, that's what we were going to do.
But you don't have to differentiate for that, do you?
That's integrate, you mean? No, that's what I was trying to do, but you guys wanted me to do it as an integral. So when we evaluate that dq, it gives us,
I agree with your way.
times q, okay? And now we know the cosine, the triangle it gave us, right, was this right triangle. That's supposed to be a right triangle, okay, of theta. We have x here and a here. So the cosine is equal to a is x. It's equal to adjacent over hypotenuse. The hypotenuse is square root of a squared plus x squared. Okay, so e of x is equal, we'll substitute the cosine of theta in with x over a squared plus x squared times k times a squared plus x squared q. So when we can do some rearranging stuff.
So 3/2.
Kx, yeah. A squared plus x squared 3/2 times q.
So there's no integral.
You don't need to. So the intuitive reasoning for this is that this value theta does not change. Charge does not change as a function of theta, because theta stays constant throughout the thing.
Yeah.
And also
Okay, look at this now, it's pretty easy.
A is the radius and a stays constant. X is the distance from there and x stays constant. So these are all constants. So integrating.
Oh, I see what you're saying.
If any of these values change, like let's say a was.
You're literally just taking the area of the circle essentially, and you know everything cancels. So you're just taking like
if this was an oval. If this was an oval, you would have to do it as an integral, because a would then be a function of rotation.
Yeah, okay, this makes sense.
Since these are all constants, when we integrate with respects to q, you just get big Q, which is the total charge.
Okay. Wait, so why would he even like discuss the possibility of doing a question like this with an integral?
On this question, well, because it is that's just the equation. On this question, actually, we'll see that it is charge as a function of theta.
You have to do with an integral because
is a function of theta because there's a charge.
Because everything cancels.
Well, not because that's not why. It's because charge is a function of theta, because for this theta here, for some theta here, charge is defined, but for some theta out here, it's 0. So that's why it is a function of theta. So when it's a function of theta, you do have to evaluate the integral. When it's just constants, you can integrate constants with such ease. You just multiply by that value.
Yeah. Okay. Wait, in the other one, there's not what's it called? In the other one, it's not like
this.
The other one, the charge is not 0 everywhere as well.
For this one.
Yeah.
It cancels out in the x direction, but not the y direction, because there's nothing.
Yeah.
There's nothing pulling down. But the reason the integral is not so simple is because it's literally just not it's a function of theta. Here.
Yeah.
Here.
Okay. I got you. Yeah. I see what you're saying. Okay. Yeah. No. So it makes sense. It's just that was the you said like when you said the other thing it was strange, but sorry, that was good. Continue.
I don't know what to
All right, Max Slowman. Don't force my boy JT to continue if he wants to do what he wants to do.
Thank you for giving me permission.
You know, you always need my permission, JT. Okay, I'm actually gonna stop.
So Max,
I
what's
don't
our
want to get
predictions
kicked.
for
I
tomorrow?
don't want to get kicked. I don't wanna get kicked.
You gotta be more worried about being clipped.
Bro, you've clipped me in a way that it literally doesn't matter what I say. Oh well, I could definitely say some bad things.
Actually, no, this one's more public.
Wait, guys, hold on. All right, I'm not. I know this is gonna get streamed on YouTube, but I have some ideas for the superlatives form, and
Ooh.
yeah, no. Have you guys submitted yours yet?
Yeah. What? What were your ideas? Yeah, I muted the live stream. What? Mr. Rosen. Yo, I said Zach Sorensi because Zach Sorensi. The most voluminous. Most dense is probably someone probably has a higher body fat percentage than you. What happened? I have no density. I have like. Yo, Max, this is gonna remind you of multivariable. Whoa, this is crazy. Look at this. So we're finding flux, okay? Flux is equal. He never explained what it means. It's a contour integral. So flux is equal to this. Look, it's equal to electric field vector dot dA. Okay. So little pieces of area. So what's interesting is let's say we have like a little cylinder, right? And it gives and we make another Gaussian cylinder over it. There's a reason we make a Gaussian cylinder because look, right? The dot product of two vectors is A, right? B cos theta. So unless theta is 0 or some factor of pi over 2, like unless theta evaluates to 0 or 1, it's super hard for us to account for the change in angle when we do math. So if we make so we know of this little object that's going to have some charge q. We know it's going to emit these little electric field lines all perpendicular to it, okay? It won't do any this way. That's never the case. We're just assuming it's going outwards in the up and that's just what the assumption we make for the sake of because it's going to be like an infinitely long wire, so it can never go out the side. Yeah. So they're all going out this way, but if you expand these electric fields, they're always going to be parallel to the normal vectors of the surface, right? Well, yes. So look, you're saying look, it's always going to be parallel to the normal vectors, right? But if we extend this wire out, what we notice is that the normal vector of this surface is this way, right? And the electric fields will be down this way. So the dot product of these is 0, okay? But the net area of that Gaussian cylinder, the bigger one, is going to be 2 pi RL plus 2 pi r squared. But this pi r squared part represents these two sides, okay? Right? But since those sides, but since it's dot dA and this is the dA, since it's dot, no, that's not why it doesn't matter. It's dot dA. This part of it is going to be, the normal vectors are going to be this way as opposed to the electric, or so, I'm sorry, the normal vectors are going to be outwards as opposed to the electric fields going this way. So the dot of those is going to be 0. So this just cancels out. So E dot dA, that's why it's really nice. So now what we do, that's why we use Gaussian surfaces. E, it's the product of these. It's just the part that's lined up. The part, yeah, exactly. That's how that works. So that's gonna, for this, that's gonna give us 2 pi RL. Yeah, I sure didn't. Okay. All right. So look at this question. This one we can solve. Oh, that's a great point. It is still muted, but let me unmute it now so people can.
Wait, no, wait.
It's unmuted.
All right, can you mute it? Can you mute it again, and then we can discuss the.
Okay, hurry up. 30 seconds. 30 seconds. Because I'm gonna do more questions. Okay, that's fine. That's fine. Anyways,
Alright, great,
okay,
thanks.
All
we're
right, so
doing
can we
this
get back to work,
So-
bro?
so
I
this
gotta study
question-
Spanish too.
So
But
flux is E.dA, okay? But it actually
Okay.
this is like really a multi-question, which is so interesting. So E here is a function of x and y, and so is dA.
Yeah.
So we
Mhm.
can evaluate so E of x is
Can you just double integral it or no? Like I feel like it'd be
yes.
easy.
Well, watch. We're gonna
easier with
evaluate
a
this.
double
We're
integral.
gonna that's how we're gonna do it. X squared plus y squared. Okay.
bro, this is
Okay.
not physics C, bro. What the hell is this?
I mean, I kind of agree that it's not physics C, but that's the question. So look dot
Wait,
dA.
but he allows us to use double integrals. Like he says you can use them and
well,
stuff.
You could evalluate it. Yeah, you could use any method as long as it
Did-
gets you the right answer.
Did he teach to do them? How do you
No.
do them without double
That's
integrals?
a great question.
Do you know how to do them?
I know how to do it. I don't know how anyone else would know how to do it. I guess.
He's
Oh,
not
okay.
giving this, bro.
Wait, so what the hell do we have? What do we even need to learn with this then?
Okay,
If
so
you're
look,
the only one who needs.
this is little r. X squared plus y is little r squared.
Yeah.
dA,
Yeah, that's r squared.
dA is gonna be well, look, we have
It's
a
gonna be
is equal
d
to pi r
r
squared.
r d theta dr.
So
R dr d theta.
dA is 2 pi r dr. So we could actually write this as
Wait.
look, A, right? It's a circle.
Oh,
Or this
R
is- this
is
is-
square root x
This
squared
is a
plus y
circle. This
squared,
is
right?
two-dimensional question, okay?
Yeah.
So
Yeah. Okay,
so
got you.
2 pi r
Oh,
dr.
I see what you're saying. Okay.
R squared.
Wait. You're only using a circle for this?
Yeah, this is not a sphere. This is a two-dimensional question. So now we have 2 pi.
No, I'm saying go away. But in no. But
Yeah.
in what's it called? In polar, the way you convert is you do
Wait, you're
um,
right. This
r
is-
r dr d theta.
So we could write A is also we could also write A is equal to big. We could also write it as dr.
Wait, JT, you're doing it right, I think.
We could write it as a dr d theta.
No,
think
r
it's
dr d theta.
RD. Is that for two
But
dimensions?
no. Yeah, well, because what I'm trying to do is
Yeah, you're
Actually, maybe this-
overcomplicating it, bro.
No. This
Do
is
it
right.
JT's way.
A is
yeah, because I guess I don't know. Okay.
A is dr d theta. We can write it like that, but I'm doing pi r squared. So we could, because pi r squared we know is the area of a circle. Okay, so we're gonna use that for now. We can go through it the
Yeah,
multi-way after. So 2 pi r dr, we plug that in there. Okay. So now we
Mhm.
get we pull out all those constants. We get r cubed dr. Okay. So that
Mhm.
becomes pi beta over 4 times 1/2 is 0.5, right, to the 4th. So that's what it
Mhm.
evaluates to. So that's one of our answers, I'm assuming, once we plug in for beta. Beta's 100. So yeah, so that's what's 2 to the 4th is 16 times 4.
16.
64
64
over
pi
100
b over 64.
Yeah.
pi. Is that close to anything? Let's see.
No, that's not right. Is it? Actually, yeah. I think it's fine.
No.
It's like 5. It's like 5, right?
Yeah. But that's not an answer. So
I think the answer is A from what I remember, but
let's
All
see.
right, all right. So here, JT, let's run this back then.
Yeah. We're gonna do
Okay.
so
Yeah, let's redo this then.
A is drd theta actually.
Wait, can you go up, please?
Yeah, A would be
Why'd you remove all that?
yeah, because JT, yeah. So I think A would have to be. Wait, no, if it's drd theta, then it's just
That's A. Think about it.
no. I don't think it's drd
Let's
theta.
see.
No. I'm telling you, it's rdrd theta because like this is how we do it in multi.
You're right.
You literally, yeah, it's rdrd theta. Because look, you have to account for the fact that it's further out as well. So that little r matters in the grand scheme of things because it's like basically a rectangle because but you hear what I'm saying, right?
I know.
Yeah, it's rdrd theta,
Guys,
right?
this is not physics C. Why are we wasting time on this?
Bro, this is physics
It
C.
is a
Just help me
physics C
understand
question.
it.
Um,
But we're
No,
gonna have to
the
do
way
stuff similar
JT
to
did
this
it
on
was
the
right. He
test.
just made some mistakes somewhere. I remember it was like that one in the solution.
beta. Okay, let's try this. So we're gonna go. So that's
Ain't
now
nobody doing this tomorrow, bro.
Okay, well, we might if this is a question, so we're gonna do it.
Yes, this is how I believe you would
It's
do
not
it.
a question, bro.
Let's see.
If he gives this, generally he's gonna make the
But
question
Max,
not
I
count.
hope you realize what just happened here is we got that same 2 pi that I got before when I said 2 pi rdr. That's the same exact thing because d theta is independent of all this. It's the same exact
Go
thing.
back to what the question is. Okay.
The question
Circle of radius 0.5
Max,
lies.
wait, look what I was saying. We're integrating d right r dr d theta, right?
Yeah. No,
But-
I
but-
agree with you.
So it's the same. Look, because d theta is independent of everything else. So when we evaluate d theta, that's just 2 pi. And I said a.
Yeah.
I said dA is equal to 2 pi.
So then
RDR.
there's
They're
just a
equivalent.
problem with both of our methods.
No, they're equivalent. But let's see where we went wrong.
No, that's what I'm saying. JT was right. You just made some mistakes somewhere.
Yeah, 2 pi. Okay. R to the.
Also, why do you know how to do this double integral method?
Why not?
Where do you learn these things from? Like seriously, where do you learn these things?
Some of it's intuitive, but
Bro, PS is not intuitive.
No. I know you learned this from somewhere. You don't know how to set up a double integral by heart, bro.
well, I just did.
You've never set up a double
I've
integral
done
before.
it before. What are you talking about?
So where did you learn how to do it before?
Give me a second.
Yeah, this kid knows, bro. There's no such thing as intuitive for this shit, bro. Unless you're like an actual genius, which he might be, low-key. Max Lipman.
No, double integrals are like, they're kind of intuitive, just the bounds are very strange.
I don't know what you're talking about, and I'm looking at my Spanish notes now because I'm done.
You're checked out.
I'm checked out, bro.
I know how to set up a double integral because it's intuitive to me how you set up the bounds. Like I'm good at visualizing 3D space because I'd spent a lot of time coding video games, like in the past.
So when did you start setting up double integrals?
When I learned integration, like as soon as I learned to integrate, like so in the beginning of like the year, maybe end of the summer. I don't know.
Wait, you learn how to integrate in calculus or no?
No, not in BC. I once I learned integration in calculus, I knew how to integrate like in the summer. I think once the calc year started, like BC, I was bored in class, so I learned how to do double integrals or something. I don't know.
You just
because that's super normal thing to do.
Well, it's because I was trying to do like something somewhat related in math class, but math class was super boring, so I just did like multi instead because I was bored.
But like you looked up how to do multi, or you just did it in your head?
Well, like some of the stuff I already knew, like intuitively, like how to convert from we learned polar last year, so you can kind of imply like x squared plus y squared is r squared, and you gotta integrate. I don't know.
Oh,
some of it I looked up.
JT,
like I would
JT,
look.
Why can't you just say you're a genius, bro? You don't have to be nonchalant.
I'm not, unfortunate. Okay, so we got the answer is 10. We did get 10. I fixed that. So the issue was when I integrated before, I messed up the integral. Just forgot to divide by 4. Okay.
Classic.
JT,
you're a genius.
Okay.
Don't let anyone tell you you're
So it was requested that I do this question. A figure shows a circular loop. Here, the one on my screen. Let me check the timestamp. How do I see that? Okay. Okay, so circular loop in a uniform electric field that points into the plane of the figure. Okay, the field is initially normal to the loop if the loop is rotated 180 degrees. The magnitude of the flux. Okay. So if we think about this intuitively, we could actually if we wanna, you know what we're gonna do? I have an idea. Okay. We're gonna show this.
Oh hell no.
So we're gonna do, let's say, okay. Actually, I'm gonna do, whoa.
That's tough.
Yeah. Well, let's say like, okay. So
How's
just
this intuitive, bro?
Just watch. Just let me. I have to set it up first, okay?
So, let a
So
master do his work type shit.
yeah, exactly. X. Z sign. I think it's something like this, but I gotta like. Oh shit. Is that right?
Whoa, no.
Let me remove this restriction. That's completely wrong. Okay. So x plus y. Oh my god, I can't even use Desmos anymore.
Wait, what are we even trying to do? What's the question again? I don't know.
So I'll show you. I'll leave the question. Oh wait, that's not the question. This is the question. I'm trying to. I know what's gonna happen is that essentially the flux is gonna start decreasing, then it's gonna increase. It's gonna decrease to 0, then it's gonna increase the magnitude.
Oh, I see how this works. Okay,
I was trying
to
like make a visualization, I guess.
Yeah. Okay, circular loop that points into the plane of the figure.
Let me do this. P equals 0.
Wait, bro, what? Is it not just it decreases and increases?
Yeah, but I was trying to make a visualization because other people are watching this and wanted to.
Well, let's really quick. I'm just checking this for my own personal thing. It's because the dot product of the angles goes to 0 when it goes like basically the way that you would turn to the side. You know how I couldn't see you when you turn sideways?
Yeah.
That's how it worked. I'm making a skinny joke, but and then it's like it looks like me when I'm turning the other way, where it just takes up all the space. The dot product is 1.
So let's I'm gonna make a vector field, okay? And so I want to, one sec, x and y. Okay. So sine t. Okay. So this will rotate now. We have a rotating loop, okay? And I'm gonna make some real quick. A is equal to let's say 5. So 0 a minus 1. Okay, so we're gonna make a vector field, right? And how we make a vector field is everything's gonna be pointing in the positive y direction. L of a is equal to mod L over. Just ignore this math. Like try and ignore it at least. 0 floor. Okay.
What? Bro, what are you doing?
Ignore it, I said.
This is not making it easier to understand. Like, not gonna lie.
That's great. That's why I said to ignore it.
No, like any of the
well, this question is not for you yet. Like it's not even for you. Like that's why it's not making any sense.
What do you mean?
Like someone else asked the question.
Yeah, and what? This is not on our test.
It could be, but I'm making a visualization first.
I hope this is on our test, bro.
So
I don't know what's going on here.
It's fine. Just chill out. Okay.
Oh.
So.
Alexa, shut up.
All right. So what we have here is this is the question. I reset it up once again. Okay. So it's asking how much flux is going through this surface. All right. And flux is going to be right E dot dA. So these red lines are going to represent the electric field. Okay. And so right now our flux is at a maximum. As many arrows are going through the field as possible, right? But now it's as if the loop is rotated about a 180-degree vertical. So let's rotate the loop. We're going to rotate the loop 180 degrees. What we'll notice is that less and less arrows, look at that, less arrows are passing through it. So now the flux is approaching 0. Look at that. Right? The arrows are all perpendicular to that surface area. So now the flux is 0. So the magnitude's reached its minimum. But now if we keep going to 180 degrees, which is roughly pi, look at that. More arrows are going through the loop once again. Okay. So that's kind of the intuitive. So it's gonna essentially it's gonna decrease and increase. Because it starts with the surface area perpendicular, then it goes like back to parallel, then perpendicular again.
Yeah, this is why I'm doing business in college, bro.
Valid.
Bro, I'm gonna be able to go to sleep at night before a test and not have to worry about some
Your test
FS
is putting
integrals type.
blocks in the right freaking shape containers, bro.
Yeah, bro. And guess what? I'm still gonna hire you, and you're gonna be my employee
No.
for quant finance. And I'm not gonna
I'm
do a
not going to
single
be your
lick of
employee
math,
for
bro.
quant. Yeah, no, actually, no, I am.
Shh. This question's good. This is good. This has valuable stuff.
Oh, yeah. Why did you get so excited?
Because we're
No, I will
gonna
definitely
actually
be Zach. We will both hire each other. Actually, Loki, should we rope JT into this?
Hey, what?
No, I'm hiring both of you. You're both gonna be working for like $500K a year. Let's
Guys,
say,
if we
I'm gonna be
all
making
guys,
billions.
Can
if
we,
any
like,
of
do
us found
this?
a quant
Can we do
company,
this?
wait, listen. If any of us found a quant company, we have to hire the other people. That's legal. That's legally binding now.
Why would I
No,
start
JP's gonna be
quants?
committing genocide for $2 million a year. So.
Yo,
I don't know.
wrong religion. Okay.
What?
Okay. A charged insulating
That's on
sphere,
stream, by the way.
I don't care, is surrounded by a concentric spherical conducting shell that is connected to the ground.
Yo, Carnegie Mellon's gonna be seeing that, bro.
Probably. A charged insulating sphere is surrounded by a concentric spherical conducting shell that is connected to ground, as shown in the figure.
Ooh.
I don't know.
Frick, does that have? What is connecting to the ground? Have
That means
anything
that
to do
all
with anything,
excess
bro?
electrons are gonna flow into ground. That's so complicated, bro.
Yeah, that's
Oh, God.
annoying.
My brain. Okay, the insulating sphere has a radius of 0.1. All right, what's it asking for? Let's see. The insulating sphere has a radius of 0.1 and symmetric charge density. Okay.
Bro, wait, this is so easy, no?
I don't know what it's asking. It really depends. The conducting shell has an inner radius of 0.2 meters and an outer radius. What is the charge on the inner surface of the conducting shell?
Not inside the surface, on the surface.
This is not nearly as easy as you. Well, it's not hard, but okay. So first, we're gonna find.
Oh, I thought it said inside the surface.
We're gonna
so
find
just
Q enclosed by that conducting sphere is gonna be rho dv. Okay. dv, and dv is equal to it's gonna be 4 pi r squared dr. Wow, someone's been studying. Okay.
I have.
So Q enclosed equals 4 pi r to the 5th dr from 0.
Froth to B.
No, oh, you're right. Okay, and where does r go from? 0 to 0.1. Okay, so that's a 10th. So that's gonna be equal to beta 2 over 3 times.
Wait, hold on. Really quickly. As someone who is a chronic non-studier, what the fuck does the inner thing have anything to do with anything?
This is the density of the inner sphere, and
It's just showing
what
you
is
what
the
radius
insulating sphere. What is the insulating? Is the insulating sphere have charge?
Yes, that's why it has a charge density function. Rho of r. That's the charge
So
density.
annoying.
But Max, if something's inside a conducting sphere, then the net flux is 0.
Yeah, it's 0, right?
Beta is 6.
Yeah.
So 4 pi.
But the grounded thing doesn't mean anything now, at least.
Not yet. Not yet, at least. We'll see.
I don't think it does.
I hope it means nothing. I'll get this wrong, but that's fine. Okay, so that's our answer for the enclosed charge of the inner part. Okay. Now it's asking for the inner.
Why is it not over 6? Oh, because beta is 6. Never mind.
This is just Q enclosed. Okay, so
yeah, I didn't realize betas cancels out with the 6.
Oh, I'm such a dumbass. My bad. I wasn't looking at what the actual question was. Okay,
So
never
for
mind.
so
That
for
makes
some,
sense.
in a conducting shell, right? The field any point inside the shell is going to be equal to 0. So the field is going to be 0 any point inside the shell. So field
Yeah.
times A or dA, whatever, is equal to Q enclosed over epsilon naught. Okay. This is inside the shell, inside conductor, right? But since electric fields, this is a property of the conductors that the electric fields within them is any point is 0. Okay.
Mm-hmm.
So
Yeah, got you.
that means that Q enclosed has to be equal to 0. So 0 equals
Uh-huh.
Q enclosed. So this is Q enclosed by the conductor, okay?
Mhm.
But the charge enclosed by the conductor, since we know charges of conductors, right? All the charge distributes on the surfaces. So that means all the
Yeah.
charge of that conductor is going to be distributed either on the inner part of the shell or the outer part, because the surfaces, right? So that's
And
what
one of them is grounded, so all the excess electrons in the outer
that's
shell
not
go
what that
down.
means per se.
Damn it!
It
It's a
means
good
that
try.
it's a net neutral. But what it means is that all the possible charges, right, on that on that shell are either on the inner surface or the outer surface. So in this case, let's say we make some imaginary Gaussian sphere and it's right smack in the middle of the conducting shell. That means that the enclosed charge is going to be equal to the charge enclosed by that insulating sphere plus the charge enclosed on the surface, the inner surface only of the conducting shell.
Wait, say that again? Well, I couldn't hear.
So we're making a Gaussian sphere that's in between the inner and outer surface of the conducting shell, okay?
Yeah, okay, got
And
you.
all the charge of the conducting shell is either on its inner or outer surface, all right?
Uh-huh. Yeah.
So what that means is that all the enclosed charge by some Gaussian sphere in the middle of this shell is going to be all the charge on the inner part of this shell plus the charge here. The charge on
Yep.
the outer part of the shell is not relevant right now.
Yeah, got you.
So Q enclosed is equal to 0. That's the Q enclosed by some Gaussian sphere inside that conducting shell. But that's also equal to this Q enclosed we found here. Okay.
Okay.
Ugh,
It's
bro.
equal to it's equal to the it's equal to the charge of of the insulating sphere plus the charge on the inner surface. Plus
And the charge on the inner surface has to be equal to the insulating
so
sphere
it's
then.
equal to 0. So it's the negation. So Q inner equals negative 4 pi 0.1.
So it was just 0 and we're dumbasses?
So we're not done. Oh, this is the answer. Wait.
No.
No, this is the answer.
Yeah, that's B.
And is
Yeah,
it
so
B?
Yeah, because 4 times 3 point something, that's like negative 12 times 10 to negative 6.
I don't know that this is right.
wait, what was
coulombs.
I asking for? I was asking for the charge of the
Inner
conducting
surface
shell?
of the inner surface of the conducting shell. Only the inner surface.
Bro, why'd you
Only
check
the
the
inner surface,
units on me, bro?
Wait,
Yeah.
how do you know that the charge of the gap thingy is 0?
The charge of this gap is 0?
Yeah.
Well, that's just because
Yeah.
there's nothing to charge it there. No, we're saying the charge, if we draw a Gaussian, right, so like we have our insulating sphere, if I can draw a sphere.
I only learned what a Gaussian sphere is when you said
It's
it.
just an imaginary. It's an
Can you
imaginary.
explain?
It's
this?
just
Okay.
we're just making an imaginary sphere and we're seeing how much charge is within that sphere, okay? So
Is this a sphere or is this
Yeah,
a? Oh, it's a sphere.
JT, I think that was the right answer.
I know, yeah, I know it is.
I just asked that.
So let's say for this object, the outer object, right? Since it's a conductor, all the net charge on the object is going to be distributed either on the inner surface of that sphere or the outer surface, but not in the middle, okay?
Yes.
So
Yes, that makes sense.
what that tells us is that if we were to make a sphere that's like directly, the radius is in the middle of the inner and outer surface, right? So it's like it's not bigger than the sphere, but it's the shell, but it's not smaller than it either. It's in between, right?
Yes. Okay.
What that
Yeah.
means is that all the charge that's enclosed by that sphere is going to be the charge on the inner surface plus all the charge in this sphere. So this sphere's charge
Yeah.
plus the inner surface charge. But what we
Yeah.
also know is that for a Gaussian for any point within a Gaussian within a conductor, the net electric charge is 0. Any net electric field is 0 for any point within a conductor, because that's a property of conductors, that the electric field within them is 0. On the surface, it doesn't have to be, but within it. So that means if we use Gauss's law, this thing here, right? Q enclosed over epsilon naught is EdA. We know that the electric field within any point is 0. So like I said, we're making an imaginary Gaussian sphere that's smack dab in the middle of that shell. So it's 0 here. So
and is a Gaussian sphere a conducting sphere? Is it always conducting?
It's just an imaginary sphere of any. So it's just an imaginary sphere that contains some charge. So like I said,
Yeah. Okay.
we know it contains the inner surface charge and we know it contains the insulating sphere charge. That's the two charges it
Yeah.
contains. That's what we have here. The insulating
Yeah.
sphere charge, which we solve for, and the inner surface charge, which we need to solve for. But we also know
Yeah.
since E dot dA is equal to Q enclosed over epsilon naught, and E is 0 for any point within that any point on that Gaussian sphere, it's 0 because any point within a conductor has 0 electric field, okay?
Mhm.
That's the point of conductors rearrange their charges such that within them, they have 0 electric field everywhere within them. So
Yeah.
if we make a Gaussian sphere that surfaces inside that conductor, its electric field is going to be 0. So 0 is equal to Q enclosed. So that means Q enclosed is 0. And Q enclosed, we also found, like, it only encloses the sphere's charge and the inner surface charge. So we found the inner surface charge to be the negation of that, and that's the inner surface charge, and that's what we were solving for. And that 0.1 to the 6 is equal to 10 to negative 6, which is equal to that, and then the units was coulombs, so it's negative 4 pi coulombs. Negative 4 pi is roughly negative 12.
So wait, what was I gonna say? So it's just
Or 13 in this case. Wait, guys, I'm checking out now, but like, thanks JT for being the GOAT as usual. LeBron James of physics type shit right here.
Yeah, how are you,
anyway,
bro? You are so good at physics, bro.
All right.
all right, Maximum
Livy,
and
can I have
best of
two?
luck. You're gonna get like an 80,
Two?
JT. I already know you're getting like 100, so it don't even matter.
I hope.
Peace, bro.
Bye.
Thanks
Is
again.
anyone else listening here, JT?
I don't think right now.
All right, I have a couple more questions then. Wait, I know I'm a dumbass. I don't know why I keep getting confused by this, but okay, what's E again? E thingy.
Electric field. It's a vector.
Okay, electric field,
that
and you know it's 0
because in the conductor, because we're
conductor.
making a Gaussian sphere where its surface is
Mhm.
on the conductor.
Its
So
surface is on the conductor.
yeah.
Oh, okay. So you're like filling out the
Okay, so the Gaussian sphere we constructed, it's an imaginary sphere. The two properties
Yeah.
we know it had, or three properties. We know its surface area, we could find it. We don't need to find it, it's not relevant. But
Mhm.
we know
Yep.
its surface is within the conductor, meaning any point on its surface has an electric field of 0. Because any point within a
Oh, it's
conductor
on the conductor.
Yeah.
Okay.
Because any
It's like inside of the
inside the
thing,
conductor,
inside of the
the
conductor
radius
sphere.
that's why
Okay.
it's an imaginary sphere, not a radius.
Oh, okay, okay.
And
So then,
any
okay,
point
yeah,
within
yeah,
the
yeah.
conductor
Okay. I
has
didn't
an
hear that.
electric field
Yeah.
of 0. So
Like
using
field of 0.
and we know its Q enclosed of this Gaussian sphere is the inner surface
Yeah.
charge plus the insulating sphere charge, and we know that its
Mhm.
electric field is 0 at any point, so its Q enclosed is 0. Meaning,
Wait, but the outer sphere charge doesn't do anything, even though it's on the inside. Even though it's on
because
the inner part.
if we were asked to solve for the outer surface, we could do that.
But we know that the outer surface charge is 0, or we don't know that.
We know that no, it's not. But we know that the outer surface is not enclosed by the Gaussian sphere because the Gaussian sphere is between the inner and outer surface.
Wait.
Look, the Gaussian sphere has
wait.
Listen, the flux of the Gaussian sphere is Q enclosed over epsilon naught, right? But the
Yes.
but the charges on the outer surface are not enclosed by the Gaussian sphere.
Wait, where is the Gaussian sphere? Okay,
the Gaussian,
is the Gaussian sphere
it's in the gray region. It's between
in the gray
radii.
region.
So
Okay,
meaning
great.
the charges
So
the
what
charges
I'm
outside
confused about then.
yeah, the charges on the outer surface are outside of the Gaussian sphere.
Is the Gaussian sphere a filled out thing?
It's just
Is
imaginary.
it like
it's not. It's hollow basically.
it
could be.
No, I'm saying is it like a ball where it's solid on the inside, or is it not solid on the inside?
It's not solid, no.
Okay. So then why wouldn't the charge on the outside of the conductor count equally to the charges? Because what I'm saying
yes,
is that
listen,
if the charge is on the inside of the conducting thingy plus the charge of the ball thingy, if those things equal 0, or if those things sum to 0, and the whole thing we know has to sum to 0, wouldn't the
no, we know that everything within the Gaussian sphere sums to 0. All the enclosed charge within the Gaussian sphere sums to 0. But like by the inherent nature, right? The insulating sphere's the conducting shell's outer surface is outside of the Gaussian sphere, meaning it's not
Okay, can you explain
enclosed.
to me what a Gaussian sphere is? I think I don't know what a Gaussian sphere is.
It's just an imaginary sphere we've constructed, and we're looking at how much charge is enclosed to it.
Okay. What? Okay.
So look.
Think that. Look where?
Okay. So all we're doing is constructing some imaginary sphere, and we're
Mhm.
saying within that inner and outer radius of let me actually, you know what I'm gonna do? I'm gonna
Help me out like a nice guy.
let me see if I can download this as a. I gotta go. I gotta cloud convert it.
Should probably study for physics more because it is interesting. Except the class is so boring.
Yeah, I agree with that.
Well, how do you pay attention? Like you
I
do all the
don't pay.
problems. Though.
Why do you think that? I'd never do the problems. My notes are empty.
But like, how do you know everything?
Well, like I just sometimes pay attention. Like some of this is review from last year.
Oh, okay. You did take 1 and 2. Okay.
Yeah, I mean,
How
actually,
are you
no.
so good
This
at
is a lot
how
harder
are you
than
so good at this specific type of calculus and stuff, and this specific type of thing?
multivariable. Like
You're just like
I told you, all those years of Roblox coding, multivariable, super intuitive for me.
really. That's great. Is that really what makes it like that helpful?
I thought it was super helpful. Yeah, I'm really good at visualizing in 3D and sometimes 4D. Not really 4D, but
How do you visualize in 4D?
I can't really, but
Well, what do you see when you try?
I see heaven. I don't know.
Okay, buddy. Well, when you do 3D, like if I told you like a plane, if I gave you like a random tetrahedron, could you like if I gave you like 3 planes and I intersected them, like would you
No.
tell me what their intersection looks like?
Probably not. I'm not like I'm not a superhero, man.
Okay.
Let me see if I can. So okay, let's see if I can download this.
6-minute timer cancelled on Echo Show.
I don't think so.
Holy fatty. Okay, physics. Okay, so we're constructing. Wow, that's huge. We're constructing an imaginary sphere. Okay, this is going to be the
Okay.
sphere. Okay.
Okay, it's in there. Okay. Okay.
Yeah.
I see.
And the definition of flux. Okay, flux is equal to
Uh-huh.
E dot dA. Okay, and it's also
Uh-huh.
equal to the Q enclosed, meaning all the charge particles inside of it over epsilon naught. They're equivalent. Okay. So
What's epsilon naught again?
Epsilon, it's a constant. It's irrelevant here. It's the vacuum permittivity constant. Okay.
Okay.
So any point within this conducting shell has an electric field of 0 because that's just the nature of
Yes.
electric fields. Okay.
Okay.
So
Yes.
so electric field 0 in all of them.
Okay, now I understand it. Now I get
Okay,
it. Now
watch,
I fully
just wait,
understand.
wait,
it.
wait,
But
wait,
why
wait,
is
wait,
E
wait,
dot dA equal to that thing?
Because that's just Gauss's law. We don't have to prove that.
Do you understand why?
Somewhat. Like I have somewhat of an. I can't really explain it well. I haven't looked at the proof for it, and I don't want to right now. I would rather wait.
Okay, well now I understand why.
Okay,
Okay,
let's,
now I understand. Now that you write that down, it's just that
E's 0.
like now it makes perfect sense. But now
Okay.
I just want to understand
But
why
look-
E dot dA equals Q
but
enclosed
look,
over that thing.
That's Gauss's law, and that's not relevant to this course. I think it's much more You could look at I've actually done some proofs before, like with the multivariable variation, and it happens to
When
work
have you done these proofs, bro? Where do you do
like for
these?
specific, I did it like I did an alternative method of solving some of the questions. I'll show you actually if you want.
Oh,
But-
actually, I do want to see this now.
Okay, but let's finish this. So Q enclosed. So let's look at this. Let's look at all the charges enclosed by the sphere, right? How do we do that? I'm gonna make a bunch of charges. So we know that all the charges on this object, we know that the sphere is positively charged. Okay. All right.
Yeah.
So positive charge, okay, and positive
Okay.
attracts negative. So we know that the net of this, so all the negative, it's going to be negative all along the surface, negative charges.
Yeah.
Okay.
Got you.
So it's going to be positive on the outside, but what we
Okay.
notice is that the positives are not. You agree that these are not enclosed by this sphere?
Yes, these
They're
are
outside
definitely
of it?
not included.
So
No. I know, JT. I understand everything
okay,
perfectly
cool.
now. You
So-
just needed to write that out.
So the Q
It's just
enclosed,
that
yeah, is the
it's just I didn't know that E dot dA, which is flux, equals Q enclosed over epsilon. But now it's
Okay.
pissing me off that Q enclosed over epsilon equals
Yeah.
that thing, and I
Check
don't know
this out.
why, and that makes me very mad.
Well, I can do it a specific proof for one specific situation.
Here, wait. Let me try here. Can we try and just have a Socratic seminar over why that is, and just talk about it for 3 minutes?
Yeah, well, let's do it with this one. We're gonna do this like a multivariable student as opposed to a physics student. Okay.
Okay.
So-
okay, got you.
So there's another definition for electric field that we seldom use, rarely use, right?
Okay.
I said.
I know what seldom means, JT.
Okay.
I read math books. Okay.
So there's another definition. You know what r hat is? R is like displacement. You know what r hat
Oh,
is?
it's the vector of
It's a unit vector.
the vector of displacement. Oh, unit vector. Oh, yeah. Okay,
So
I know what that is.
these forms are going to be equivalent. I'm going to write both forms to clarify this. Okay.
Okay, got
So
you.
we have these two equivalent forms. Okay.
Got you.
And
Oh, this is reminding me of curvature.
but well, curl of like of a field. That's not exactly. That's a cross product. That's like, what is
Or
it?
curvature. I don't remember.
Cross
Yeah, you're right. No, I just know r cubed is something strange if I remember
Did you guys
correctly.
even learn curl?
Matt, we learned curvature. Is curvature and curl the same thing?
I don't know. I'm not sure. But curl is
Okay,
this.
yeah, I don't-
It's this cross product.
Oh,
Did you see this?
I think we learned something similar to that.
Yeah.
It's a cross product. Yeah, I believe that's what I think. I think that's what we learned. It was at the
That's
very
curl.
beginning of the year.
That's weird that you
I,
would
I
teach it.
li- I literally haven't paid attention to that class
Okay.
ever.
So
I
we're
hate
gonna
that class. It's so
we're gonna
dumb.
define.
Wait, JT, you don't understand how boring multi is. You're lucky to not take it in Roslyn.
I would have taken it and probably found it somewhat interesting.
You actually, well, you're different. Sorry, continue. Anyways,
So the electric field. Let's say there's a. So this is so r is going to be actually the displacement of any given test point. So p is the test point relative to the
yeah,
charges.
gotcha.
So like, let's say we have a charge over here, right? Charge down here. The r is going to be that vector, like towards that position.
Mhm.
Okay, so that's our r. So we can write this. We can parameterize it. Actually, this is dq. Really, it's dq. Okay, dq.
R or R hat.
Either. These are equivalent forms. I want you to notice these are equivalent forms.
Yeah. Oh, yeah. Well, no, I see that. It's just R hat is the direction up to the point, not the thing to the
Well,
point.
r hat is equivalent to this. So these are
Yes.
that's
Yeah, of course.
So I'm
Okay,
gonna
yeah,
use
yeah.
I'm gonna use this one actually. So this is what we're gonna use. But instead of q, we can write like dq, like integral dq.
Okay.
So we're gonna write r as a function of. We're gonna make a new variable, and we have to make a new variable called phi.
Okay.
And phi is the rotation this way. Does that make sense? Like
Uh-huh.
it's not theta. It's actually going like, how do I show you? You know what I
Yeah.
mean? Like into the
No,
other
yeah,
plane.
yeah. You're like it's Let me think of the best way of describing it. It's like it's theta the other way. It's theta like.
So
Yeah.
E is going to be equal to. So actually, let's write R first. How can we write R? So R is going to be this displacement here.
In terms of phi.
In terms of every variable. So R, if starting from, let's say we have some test point up here, okay? Some point here.
Also dq is the little piece of charge, is what you're saying on the thingy.
Yeah. So our x displacement is going to be positive x, right?
Yeah.
Actually, that's not always. Yeah, that's always true. Okay. Now our displacement on the y-axis is actually going to be dependent on phi. The radius is a.
Yes.
But we're going to make it. It's going to be a cos phi.
Okay.
Does that make any sense? Because look.
Yeah. No, that makes sense. You know, it makes perfect sense.
A sine phi. Okay.
Yeah,
so
and then it's gonna be a sine phi for y.
So
Yeah,
that's
yeah.
y and 0.
Also, wait, where did you learn this one? Is this one like? How do you find out this one?
I just intuitively did this one. So we're gonna go on with this. So if we actually take the magnitude, what's the magnitude?
No, I'm saying like is the definition you gave a well-known definition?
Oh yeah,
or is
it was in the notes somewhere, I think.
Oh, okay.
But he doesn't actually go over it because it's too complicated for us.
Okay.
But I think it's a better approach. So if we take the magnitude of this, x squared plus a squared cos squared phi, right?
Plus, is this the thing you were talking to him about?
A squared sine squared phi.
Yeah.
So check this out. We can factor out that a squared, but cos squared phi plus sine squared phi is 1, right? So that's just the magnitude of this vector simplifies to x squared plus a squared, okay?
Yep, okay.
So I'm gonna move these facts all to the side. Okay, just.
Yep.
So that's we found a lot of important information. So we actually have everything we need already. So E, and this we don't have to do any we don't have to do symmetry arguments until later. Okay. So.
Well, there's no symmetry. You don't need to do symmetry because you just set up the whole question.
If we did it without multivariable approach, you would need symmetry to say like this direction.
Yeah. I'm saying you shot it in one go. You're good. Yeah.
Yeah. So K, dq. Okay, check this out. Over. So now this is where you get the 3/2 from. R is this, right? It's rad this, but in this definition we do we cube it. So it's rad x squared plus a squared 3. So that's the 3/2. Okay?
Uh-huh.
And then we put r on top and dq.
Yeah.
So we have
Yeah.
x a cos phi a sine phi. Okay. And we have dq. Now we're gonna use density just to complicate this, to make it for the symmetry argument, or arguing that, like, let's just do it. So lambda is gonna be our linear density is equal to dq over dl. Okay.
Mm-hmm.
And now L is gonna be some little piece of circumference, right?
Okay.
How can we find L? L is gonna be equal to what? Radius A times what? A times phi.
L
No,
is equal, yeah, A times 3.
wait, is it?
Wait, what?
No, it's A times theta.
No.
Yeah, it's A
Mm.
times.
Oh, arc length, yeah, it's A times theta.
Wait, no, it's not. It's arc length.
Wait, no, it's not.
Okay, you know what
No,
it's A times phi.
it's
A
X times theta. Wait,
no,
no,
but
what the fuck?
but
Yeah,
look, it's rotating around this way. This way is angle phi.
Mhm.
So it's actually
I'm
A is the
tripping.
radius times phi. Okay?
Mhm.
So dl is going to be equal to A d phi. Okay? dl is A d phi. I'm going to just keep this like super concise by removing this. So dl I'm going to substitute with A d phi, or d phi, however you want to say it. Okay? So we can plug in so dq is now equal to lambda A d phi. So we have dq in terms of other variables. Okay, so we're gonna remove dq here. We're gonna plug in dq, all this stuff. Now we have a bunch of things here. Okay, this might be hard to read, and I'm gonna try and write smaller. Okay, we have we can pull out this a. Really interesting. We can pull, let's do that. I'll pull out lambda a. K. So we have k lambda a. K times k a. All right. Now when we integrate this with respects to phi, okay, obviously it's gonna go from 0 to 2 pi, right? And what's the integral of cosine from 0 to 2 pi?
Oh, fucking what, 1 or something?
No, it's 0.
Oh, it
Likewise,
is 0.
likewise, what's the integral
So
of
is sine,
check
because they're.
check this out.
Oh, that's so clever.
The integral of sine from
That
0
is
to 2
so
pi.
clever.
So
That
now-
is really
so check
well
this
done.
out.
I love
We're
that.
not even done. So now we're gonna get all of this, right?
Everything cancels.
Well, not quite.
Well,
Not yet.
you just get the one coordinate. You prove that everything.
We got 2 pi x comma 0 comma 0. Okay.
Very well done.
Over. We're not done though. X squared plus a.
I'm not saying very well done like you're done. I'm saying very clever.
But now we can actually solve for lambda. Lambda is some uniform density. We actually did a uniform density, which is equal to the charge q that it gave us over the arc length, which the arc length here is going to be a times 2 pi. A times theta.
Oh, but lambda is uniform though. It's not
So
variable.
that's why it's not a function. It's a constant. So we can.
Okay, good.
Look, we have a 2 pi here. We're gonna replace lambda with lambda becomes q over a 2 pi. Check this out. We have a 2 pi here. This cancels out with this. And we have an a here. That cancels out with that. Okay? So now we have this shouldn't say dq. So well that's dq. Okay. So now we have
over
now we have e as a vector is equal to q k x. I can just write it like this: 1 comma 0 comma 0. I'll just factor that all out.
R to the 2/3.
Over well the r is gone. Well, it's r to the 2/3 exactly, but we could also just do x squared plus a squared to.
Yeah, it's fine. Wow, very clever.
It's 3/2, not 2/3.
It's very clever, JT. I like that way.
Yeah. So yeah, and the next question, this one's an even more awesome integral. It's a u sub. It's the same exact thing.
The only person in the entire universe who would describe this as awesome.
Okay, so look,
Continue.
it's the same thing, but this time I'm actually check this out. I'm gonna copy all this over and hope like it's not even legible at this point, but who cares? Okay. So now
ruined my entire day. Okay.
Whoa, why is it invisible? Oh holy. Oh, this is all the work. Okay, So it's the same thing as before, but instead of lambda, we're gonna have a two-dimensional. This is actually a pain. This is a pain to do. I'm thinking. You know what? So check this out. Now it's gonna be rho. It's not rho. It's sigma equals dq over dA. This is where it gets awesome. We have dA here. So dA equals this dq. And remember how like going around this way is phi? Okay, great. So we're gonna do that same thing, and then we're gonna have r. So now dA is equal to, I think it's just dr d phi. And the reason is because phi, like if you just evaluate this, phi is gonna go from 0 to 2 pi, so that's like 2 pi dr.
Yeah.
I think that's right. Actually, it's probably not. It's r dr d pi d phi. Okay, I think that's right. So now we're gonna substitute dq in with sigma dA. Okay, so sigma dA, and dA is gonna become, yeah, okay. So
Yeah, RDR d theta or RDR d thingy, right?
yes, so exactly. I think that's right.
But you did that intuitively? That's impressive.
But let's finish this. Oh, you know what the issue is here? Now
What?
this is not A anymore. This is no longer A. Check this out. This is R. This is R.
Okay.
Because that's the height in the horse. Because R could be here. It could be up this high, or it could be
Okay.
or it could be up here. So it's actually little r now. Like, see how we have dr here? That's dr. So it's
Yeah.
So it's little r here, and this is not A anymore. But we know that little r goes from 0 to, it goes from
Wait.
0
Where's DR?
So dr, look, this here is dr.
Wait, we're trying to find the charge of the blue thing or no?
At the P we're finding the electric field.
Oh yeah, we're trying to find the
Blue
electric
thing
field
is
of
a
the blue
little
thing.
ring, dq. Yeah.
Okay.
So instead of, like, see how in this previous question we had A, where A was the radius? Now the radius is variable from 0 to A. So we replace it with little r because we're going to do a dr. So we have a dA here, and dA becomes r dr d phi. Now it's r dr d phi, but we have to set up new parameters. So dr is going from 0 to big R. So 0 to big R. D phi, but actually I'm gonna switch the order. We're gonna do it d phi dr. It's actually gonna work better. We need this argument because otherwise the integral will be impossible to solve. So we actually want to switch the order, and that's okay because they're independent of one another. Okay, so remember we did before d phi. Look at this. Remember how we did like the integral of cosine from 0 to 2 pi was 0? This is by the way, this is r sine. The integral of sine from 0 to 2 pi is also 0. So when we integrate that next part, also there should be a k out here. I realized that. Okay, so this is gonna be equal to k sigma 0 to r. But when we do that integral, that 2 pi is gonna, this vector is gonna be independent of phi, so it's gonna evaluate to 2 pi x. So 2 pi x. But when we integrate cosine of phi with respect to phi from 0 to 2 pi, that's going to be equal to 0, 0, 0, times r dr over, like before, x squared plus r squared to the 3/2, okay? So this r dr is still here, but these two canceled out because the integral of cosine and sine with respects to phi from 0 to 2 pi is 0, and x d phi from 0 to 2 pi is just going to be equal to 2 phi. So that's what we have left, okay? So now, check this out. I'm going to rewrite this integral like this. I'm going to take the 2 phi x. I'm going to leave that there, but I'm actually going to write the vector. I'm going to pull the brackets out. So that, so I'm just pulling the brackets. E is equal to comma 0, comma 0. So I just pulled the integral into the brackets.
Okay.
Because I can. Now, r dr. Check this out. We have to integrate with respect to r dr. Let me write that slightly better. So we have R here and we have R there. How do we solve this integral? There's a simple
R where and
way.
R where?
We have a little R here and we have a little R here, and we're integrating dr from 0 to big R. How do we solve
U
this?
sub.
Yep.
U sub.
So let's do U. I'm just gonna write it out anyways.
I feel like this is more complicated than it should be.
Well, we're doing the multivariable approach.
Okay.
Okay. So now when we rewrite E.
Have you done this before or no?
Yeah.
Or is this your first run through?
This is like my second run through, I think.
Okay.
So what this is gonna give us is gonna give us, we have a 2R here, 2R, okay? So that's gonna give us, I'm gonna pull out the pi x actually. X. So when we plug 0 in for R here, it's gonna give us x squared on the bottom. When we plug big R here, x squared plus R squared. Now we sub in the U to R dr is equal to du. So that's gonna give us, I pulled out the pi x, I pulled that out. 1 over
Okay.
U to the 3 halves du, comma,
There you go.
0, comma 0. Yeah. Now that's just gonna give us a negative, which we actually want. Negative 2 pi. Right?
And we're back.
Yeah.
Essentially to where we started at the other one.
What's important to note, K sigma, okay? This is like if you wanted to argue that DQ is not independent of all that stuff, like this is, so what this gives us is, let's do this real quick. 2 pi K sigma x. Now when we plug in, this is gonna become, this evaluates to negative 1/2, so that's rad 1 x squared plus R squared minus 1 over x, I believe. Yeah. Comma 0, comma 0. This is our final answer. We can also substitute sigma is equal to dq over dA, so that's q over a, and a is going to be pi r squared.
Mm-hmm.
So that's going to become q over pi r squared. Yeah, that's the final answer. Really kind of stupid answer, but
Pretty good.
and what's important to note, this has a negative direction.
Okay. Odd.
Why does it have a negative direction?
Because
I probably messed up the signing.
Don't worry about it.
Wait, I'm actually curious why it has a negative direction. Oh, you know what it is? I don't know what it is. Okay, because this is actually less than this. So this part will evaluate to negative, and then this negative will cancel out with this if we flip this around. So this evaluates to negative. So it actually has a positive direction.
Okay.
So it does give us a positive value.
Perfect. What was I gonna say?
Couldn't tell you.
What else do I need to know for physics?
I don't know.
I'm gonna look. Can you just do a couple more of the normal questions from the AP classroom?
Okay. I guess it depends on what we call normal, but oh my god, it's lag. Whoa, what the hell? Bro.
Do you first free?
What happened? No. I have nothing. I only have 5th free tomorrow.
Oof.
Yeah, I could pull up the multi and teach you physics. I don't think Mr. Lee would like that very much. What if I use multi to teach the physics? Now that's big brain. He might recognize that. Like if I take what you're learning and apply it to, what are you learning? Oh, you did triple integral. We could actually apply it to this if these were 3D situations. Okay. What the hell does that symbol mean? 2 solid spheres, both have the same radius as shown. The spheres are far apart, both in electrostatic. I always forget the definition. Let me So
probably no electrons are moving.
It's a state in which charges in a conductor are stationary. Yeah, so E is 0 everywhere inside of it. The spheres are far apart from each other. Okay, there's a net charge everywhere within the sphere's volume. A charge plus Q uniformly distributed throughout the top half of the sphere, and negative Q uniformly distributed throughout the bottom half. Bro. As indicated, there was a downward electric field in each sphere at the point. How are they in equilibrium if there's...
I have no idea. Yeah, I don't know what the fuck this is. This is such a weird question.
Do you have, like,
Um,
ChatGPT credits?
Nah, you don't have premium?
No, bro, I'm not a cheater.
I have premium.
Can you, like, screenshot this and put it in?
Sure. We should try and get this though. Although I
Okay,
want to
sure.
see why Gauss's law is true. Do you understand why Gauss's law is true?
That's like, can we, like, do that after this test is done? Like, on Friday or Thursday afternoon?
That is not what I want to do on Friday, bro.
Okay, bro. That's for another time. There is a nice way to prove it. We can use the, well, like for single point. Let's say we have a sphere. I'm thinking, right? Let's say we have a sphere, okay? Radius is like some, this is a sphere.
It's called the God equation, I think. Gauss's law.
Okay, let's say we have a sphere, some radius of 4r.
Okay, here I'm going to take this from ChatGPT. Charge is distributed throughout the volume. Q plus uniformly in the top half, Q minus uniformly in the bottom half. Non-zero downward electric field at a point inside of the sphere.
So that means it's not a conductor.
It's sphere, yeah. If sphere 1 was a conductor, free charge would move until the electronal thing becomes 0. So sphere 1 must be an insulator. Sphere 2, charge exists only on the surface. Q plus in the top half, Q minus in the bottom half. The interior contains no charge. There's a non-zero electric field at a point inside.
There's a non-zero inside.
Yeah, now I'm confused.
What
It
does it
has
say?
to also be an insulator. They're both insulators.
Oh,
That makes
because-
sense, though.
I
I think that makes sense.
think so.
Okay, now I'm gonna look up why Gauss's law works.
Okay, wait.
Let's
I was doing a proof that I think will work. Okay, so we have a
In general,
Yeah. So, well, we're gonna prove it for a sphere, and it theoretically holds for everything else, I think. So
because you can integrate the littles, because you
okay,
can
so
sum
let's
up
let's do
littles.
it. Ready?
Wait. Is this because you could sum up a bunch of little spheres
Yeah.
and
yeah,
like
probably.
get to everything else?
Probably something like. So we're gonna have a point of charge Q, and it's gonna be 1r away from a sphere of the center of a sphere of radius 4r. So it holds that. Oh shit! This is gonna be horrible. This is gonna be horrendous. I don't even know how to do this. Oh my god! What am I doing with my life?
What do you want to do with your life, actually?
Not this.
You want to do computer stuff?
Probably. So how do we find?
Software engineer?
I'm thinking. Oh, this is horrible, dude. So we have to sum up all the little pieces of area, dot product of.
With respect to
a point that's offset.
Offset from the sphere?
So like, look at it this way. You could represent E as a function of like x comma y. Like where
This is the electric field at a certain point, okay?
Yeah.
And wait. So this is a sphere that's uniformly charged. It's a conductor.
Yeah.
So it's uniformly charged. So, or not uniformly charged. So the charge internally is gonna have to sum to 0.
We're doing it for an insulator. It's an insulator.
Wait, Gauss's law also works for insulators?
Yeah. Well, it's
Wait,
primarily
what's the
for
law again?
insulators. So we're doing this. Look, so it's a vector. So it's going to be a point here. So the charge is going to be a position. I'm going to position of the charge. Okay, we're going to let it be negative r comma 0 comma 0. Okay, so that's the position of the charge. So the relative position r of anything relative to that, r is going to be equal to like that position minus p of q, the relative position. So it's going to be equal to r is going to be equal to x plus r.
Yeah, JT, this one you can do with multi, because you could take...
I'm doing it right now. So x plus r y, z, okay? And then our magnitude is going to be a nice, horrendous x plus r cubed. Oh no, squared plus y squared plus z squared. We're going to try it and see what becomes of it. Okay, so it's all of this dq, okay? dq. And we're going to say, well, actually, it's not uniformly distributed, is it? Now,
the charge doesn't have to be uniformly distributed, right?
well, what do we convert dq to? I guess a little piece of
I think it would just have to be a little piece of the charge density at every point.
yeah, but the charge is only at one point.
Wait, okay, so now how does Gauss's law only works for charge at one point?
No. But I'm saying in this instance we have a point charge.
Oh, okay, you're just proving it for this very special case.
Well, but this should apply to all cases because you sum up integrals.
Yeah, okay.
Let's see. But what would dq?
You came up with the idea of doing it for little pieces?
Well, that's what an integral is.
No, I'm saying, okay,
I didn't
that's
come
fair.
up with anything. I'm just applying it in unique ways. What would dq be? Would be, I'm thinking.
If it's the charge density of a certain point, then it's just infinite at that point, then zero or else, no?
Well, it's one sec, dq dot dA. That's what we're missing. Dot dA. Yeah. I guess it's zero it's at zero everywhere else.
You know that function? What's it called? The
You're thinking
gamma
about the one
function?
it's not the gamma function. You're thinking about the function that has an area of like supposedly 1 or whatever. But it's infinitely
The one with the
tall.
frequent, yeah, that one. What's it called?
That's
Lambda function.
I don't know. It might be lambda. No,
Dirac delta
it's
function.
Dirac delta.
Yeah.
Oh my god.
No, that is what it is. That's what it is.
Well, this is a.
It's a delta function. That's what it is. I think that's the answer. I think that's what it is.
Well, this is just gonna be q when x, y, z is equal to 0. Oh, check this out. Dot dA, but this is only it's gonna be 0 when it's only gonna be x plus, oh my god, x equals negative r, y equals 0. This is so confusing. Let's ask ChatGPT, because I can't think for myself. I was thinking about how to do this, but I can't really figure out a good way. Let's see. Let's see what GPT has to say for me. I think this is the same setup I did. R minus R0, yeah.
I'm telling you, it's going to be the Dirac delta function.
Oh, look at this. We have whoa. Is that what this is? The Dirac delta. Oh,
I'm telling you, that's definitely what it
that's
is.
what it is.
Yeah, dude, of course, because that's the only
Yes.
thing. Think about it. You integrated the
Yeah.
charges.
Oh my god. Wait. Let me see this. Apply the divergence.
All right, I'm actually so happy I got that. Okay.
I thought I was thinking, and I'm like, what the hell?
Yeah.
Let's see. F of R.
All right. Finally, I've gotten something in physics that's interesting.
I don't think this is remotely related to what we're learning.
Dude, this is so unrelated to what we're learning, but at least we came up with something interesting.
So F dot dA is equal to the gradient F, but times. Oh my god, the gradient times F dV.
Yeah.
That's divergence theorem. Oh, that's converting from a 2-dimensional to 3-dimensional. What the hell? Oh my god. I'm sure. I don't think Mr. Lee's taught this.
Bro, Mr. Lee has definitely not taught this.
And it's
Bro, all right, this is something we'll come back to later. When you come over, we'll come back to this.
Wait. I want to see this real quick. Equals 4 pi Dirac delta of R minus R0. So it's only going to be equal to, like, okay. Since the charge... Oh, now we're integrating Dirac delta. From dV is equal to 1. Since the charge... Oh, I think this is flawed, but... Oh, that's just equal to the surface area, I guess. I don't know. This is not perfect.
But the Dirac delta function is the correct way of doing it, though.
Yeah.
Which is crazy. That is actually so insane.
I'm praying no one watches this live stream. Imagine you watch this and you hear Dirac delta function, and then someone just jumps off a bridge.
Wait, let me find the live stream on YouTube. I want to watch this.
Look at this. I made a 3D visualization of electric fields.
Bro, what do you have the free time to do this? Unironically, how do you have the free time to do
I
this?
did it during physics class, and then I do it during BC. Look, these are tangent normals and binormals of a function. Also,
what do you do when you get home, though? Like, deadass, what do you do when you get home?
Not this. I was playing guitar.
You just do this in school?
Yeah, it's like a 5-minute craft. Like, this is a 2D
That's
version.
crazy.
This is like 2D version of tangents and normals and binormals. But oh look, I made solid revolution. I did this during math class.
Yeah.
Look, solid of revolution. It's a bunch of like stripe like areas.
That's pretty good.
Cut up.
It's pretty good.
I made Mr. Carmen one time. He was showing that to everyone.
Yeah, look, I'm looking at the live stream now. Just join the live stream. I want to see how good this is.
Oh, look at this.
Oh, that's so trippy.
What? This is 3. Yeah, this is 3D tangents.
Wait.
What else? Oh my god. Oh wait. Perlin. Do you know what Perlin noise? You definitely do.
Do I know what is?
Perlin noise.
No, what is that?
It's this. One sec. Let me fix this actually. I had like faulty formulas. Oh, is that still faulty? Bro.
I rewatched our talking at like the hour and a half ago.
Mm-hmm.
That's so weird. That's so trippy, actually. This is all recorded.
Yeah.
All right, anyways, block the recording from the YouTube video now, please. I think it's time.
Okay, one sec. Oh, wait, that's what the issue was. One sec. Is that wrong?
Let's go look at how to do text files on my freaking stupid comp site. I hate
What were
comp
you
sci.
saying?
It's boring. Can you turn the stream off?
Okay.
Like for YouTube?